project overview and discussion. Hello everyone, welcome to this amazing section where you will learn how to create an aircraft only by yourself. I prepared for you a specific workbook that you will see step by step how to develop any type of aircraft that you desire, and we're here actually going to complete our first project. But let's move on to the slide where I will discuss a little bit what are the different stages when you're trying to design an aircraft from a given project. So a design of an aircraft could be quite overwhelming, and this is because the aircraft is quite a complex vehicle. There are many different types, many different requirements to the aircraft that you need to meet while you're designing it. As a starting point, we're going to look at statistical analysis, or once you get your first project, you want to see similar types of machines or similar types of aircrafts to your and record their characteristics, and then see and explore what you can improve in these previous projects. When initially designing your aircraft, you need to decide how much fuel you're gonna use, how much the aircraft weighs when it's empty, what is the number of passengers. Actually, you will be given a project so you will know the number of passengers that you need to create aircraft for. Also, there are different types of aircrafts, like military and civil ones, which have different missions. So you need to investigate what is your mission, what exercises your aircraft is going to complete, and design it specifically for that mission so you're effective and the costs for operating and creating your aircraft is as low as possible. Then you will need to decide how many engines you want your aircraft to have and estimate the thrust required for your aircraft to safely take off and land while having the maximum number of load and passengers. You will then need to decide what are going to be your control surfaces, where is going to be positioned your wing and your tail, estimate the balancing characteristics, and design the cabin, whether it's going to be a business class or it's going to be an economy class, just by yourself. These are all the necessary things that an aircraft designer should think about, and this is why I'm saying this could be quite overwhelming. So let's take here an engineering approach and just perform them step by step. So typically when a company gives you an aircraft design project, they don't give you much of information. They would usually say that they need an aircraft that have certain takeoff mass, for example 13,000 kilograms. They will tell you the number of passengers and the range that they want this aircraft to cover. And actually what you can see in front of you is an overview of the project that you are going to be designing. Yes, here we're talking about a business jet that will carry about 12 passengers with range of about 3,500 kilometers. So basically, only knowing this information, you need to design the rest of the characteristics and the qualities of the given aircraft. So yes, there is not much information as you can see, but once you read the guide and once we go through all the stages of the aircraft development, then you will find out that it's actually not quite hard. So for this project, we are going to use one technique, which is called the evolution technique. It is a very common technique, especially when developing an aircraft that is not actually a completely new concept like air taxi or some space drone. So what we usually do, we take statistics, we take parameters from already existing aircrafts that were developed in the past, and in the beginning of our project we approximate the desired mass for our aircraft, see the engines that the air companies were using, and check if they are new and more improved engines of this type that will not only enable our aircraft to fly safely, but also give it a slight improvement from the rest of our competitors. Also, we will need to investigate the newest components that are available this year. So the past aircrafts, they were developed in the past. So this means that at that time, the technology was not as advanced as today. So we don't only need to see their parameters, but also try to improve each component using the new materials and the achievements, the current achievements in the aerospace technology. And actually applying the evolution technique for every aircraft, we can see how certain type of aircraft has developed throughout the years, how certain modification of aircraft developed with the new technology. So it's quite easy to follow the tree of improvement of any aircraft type in that way. This is why this technique is very common, and it's one of the most commonly used techniques for designing, creating, and manufacturing today's aircrafts. So inside the resources area, which is attached to the first lecture of this section, which is actually this lecture that we're currently having, you will find a few things. You will find your workbook for aircraft design, which is this one, okay? And also you will find the project one. And in the project one, you will find the Word file where we're gonna write and include all our tables and explanations for the business jet that we're going to develop, and we're going to use an Excel spreadsheet to complete our estimations. I don't want you to spend hours and hours of estimating complex mathematical expressions for the aerospace parameters. Today we have computers advanced enough to perform these calculations instead of us. Okay, so we are not a calculator, but you have one. So for that reason, we're going to use Excel for all our calculations, and you actually see how easy it is to apply the complex formulas in Excel and then structure our project way easier. Okay, so you have these two files, but let's look at the workbook and check the project that you are having for the next sections and for this course. Okay guys, so here's your workbook, and as you can see, we're going to start with the statistical analysis, but about them I will talk in the next video. But what I want to concentrate on is the actual project that you are going to be having. And this is going to be in the bottom of the document. So here is your project. Your project is to design a civil aircraft that is of a type business jet. The aircraft should allow increased cabin space for all passengers, or business class will be the only available class on this aircraft. But let's see the most important things, and basically the things that we care about when we start our designs. So we want this aircraft to be for 12 passengers. We want the wingspan to be 20 meters, and this is because our company wants the aircraft to be able to land on more types of airports, okay? And the wingspan is important requirement for some airports in order aircraft to be allowed to land there. We're going to operate into the transonic region. I actually have a course for transonic aerodynamics if you're interested on what is transonic aerodynamics and what is transonic speed. So we are operating in a transonic region with a maximum speed of 980 kilometers per hour. It could be lower, but it shouldn't exceed 980 kilometers per hour. So our aircraft can fly over cities and basically inhabited zones and doesn't make too much noise. The maximum height of the flight shouldn't exceed 15,000 meters, which is flight level 500, and also we want our range to be at least 3,000 kilometers, and we're actually going to design it for 3,500 kilometers, as this aircraft is going to be for relatively short distances and flights from city to city for business company members. And finally, another requirement for you to be able to take off and land from certain airports, the takeoff distance shouldn't be more than 200 meters. Usually the takeoff distance is way higher than the landing distance. For that reason, we added only requirement for the takeoff distance here. And this is your project, and based on this data, you need to create your new aircraft. So that was, guys, for today. I wanted to introduce you here to your project, and I will see you in the next lectures when we're going to start to talk about the statistical analysis. Hello guys, today we are going to talk about the statistical analysis and basically what is statistical table. As we talked in the previous lecture, usually you need to take a data from already existing aircrafts, and normally designers are taking 3 to 5 similar aircrafts with the similar characteristics to the ones in their project, and they're basically recording and writing inside a table their main parameters, and basically parameters that can be used in our project in order to build the initial assumptions for the future aircraft. There are some parameters that are difficult to take, so usually you can search for drawings for these types of aircrafts, but bear in mind that you need to have a scale factor on these drawings, so you can basically measure the dimensions of the aircraft and then multiply it to this scale factor to get the real dimension. So in these statistical tables, you need to always include as new aircrafts are possible. Because if you only include aircrafts that were built, let's say 30 years ago, maybe already an improved version of these types of aircrafts has been developed. So you will be building nothing new. For that reason, you always need to search for aircraft into the last 10 to 20 years. And yes, this looks like a big period, but for the aircraft validation and development, this is actually not that much. So here we are in our workbook, and as you can see, this is our first section. And basically here the text that you can see is quite similar to the one from the slide. So we need to start to work on the 3 aircrafts that we're going to use for our statistical analysis. And these are the parameters you need to cover. You need to cover parameters related to mass, geometry, flying capabilities, and power plant. Power plant, these are basically the engines and how they are developed. You also need to record the name of the aircraft for future reference and the country that was built. Also here you can include the name of your aircraft, and actually I'm gonna give a name to our aircraft. So I will take this table and I will copy it with Ctrl+C, and I will go to our project 1. So this is the project file, and here we're going to start preparing the statistical analysis. So I will paste the table and we're going to start to fill our table now. So the first thing you need to do, as you know the requirements for your aircraft, you are going to search for aircrafts that have 12 passengers or around 12. They could be more, they could be less. You need average data. It is very hard to find exactly the same aircrafts with exactly the same parameters that were given for you. So let's first name our aircraft, and I'll actually name it Business Fly, okay? So because it is a business jet, so I think it's quite a good name for aircraft. And it is important to note that once you record the data for your statistical aircraft, then you can fill here an approximate numbers for the parameters that you think or you estimate that your aircraft will have with its number of passengers and weight. So here on the web I actually found 3 aircrafts that are quite similar to the business jet that we're developing here. And these are the Dassault Falcon 900, Learjet 45, and actually the most amazing Embraer Legacy 500, which are all business jets. I would say the Embraer Legacy is the most renowned and advanced business jet comparing to the rest. So I will start recording their characteristics, but first I write their names in the table. So let's write Dassault 900. Actually its code name is Falcon, so I write it here. And the country of make is France. Then for the second aircraft I will actually just copy and paste them so I don't waste your time. It's Learjet 45 and it's built in USA and Canada. I advise you to search these aircrafts on the web and just record their parameters while I'm doing this as well. And the final aircraft is the Embraer 500. And Embraer, if you don't know, is developed in Brazil. And that's it. So these are all the aircraft that you are having. And now let's start filling their data. So here you can see for Falcon 900, I found in their website that there are quite a lot of parameters and typical weights for them. So from here, I will start recording all the masses, the geometry and so on. So the takeoff mass, so remember, here we're actually recording our masses in kilograms, okay? So we're using the C system. And you can see that in many sources, as there are many aircrafts with the American standard, which is normal, they record it in inches, feet, and lbs. So I already estimated and recorded these values, and I will just write them like this here because there is no point to transfer these values in front of you. You can do it by yourself, or you can just write the values that I already have and use them later on in your project. So the takeoff mass is 20,000 kilograms. The number of passengers of this aircraft is about 19. So this is like the maximum number of passengers that I found. The mass of the empty aircraft is about 10,255 kilograms. Then the fuel mass is 9,482, and I couldn't find information for the wing loading, so we're going to leave this empty. Then the wingspan of this aircraft is 20 meters. The wing area is 50 square meters. The aspect ratio of the wing is 8. The aircraft length is 2.5 meters. 20 meters. And the fuselage diameter is 2.5 meters. So just to mention that one of the sources is obviously the company website, but the other source that I used is basically the Wikipedia page, and Wikipedia sometimes is quite useful about these things, where in the end usually you can find the specifications of different type of aircrafts. Okay, so this is what I used. I basically used Wikipedia and the site of the producer. Okay, in here obviously you can find drawings and also recorded data, so I just took it, and if it was recorded in feet, I just re-estimated it. So the minimum speed here is 158 kilometers per hour, then the maximum is 950. The range of this aircraft is 7,400. The maximum flight height, I couldn't find it, so I will just write a dash here. Then the takeoff distance was about 1,560. The landing distance was 715. And then the engine that I found to be used for this aircraft, and actually for most of the business jets, so apparently all of the business jets actually are using the Honeywell engines. And this one is using the Honeywell TFE 73160. And here you can actually see it in their website, okay? And once you have the engine, you can actually search for this type of engine in Google and find its thrust, takeoff relative thrust, specific fuel consumption, and so on. These are parameters that you can find for the specific engine, and normally they are not going to be included in the website of the certain aircraft. So you can see here I simply assessed the Wikipedia page of this engine, and here you basically can find most of its parameters. Also, you can check the website of the manufacturer. They usually have lists of the tables with all their engines that they are producing and with the specific parameters for buyers. But first of all, let's record the number of engines, and this aircraft has 3 engines. The takeoff thrust, I calculated it in the DA newtons, so it was about 6,672. And then the takeoff relative thrust was about 0.32. And the specific fuel consumption I couldn't find for that engine. So you can actually see the specific fuel consumption is here. I just transferred it to this dimension here. Actually, let me remove this bracket. Sorry, I meant the relative thrust. And the specific fuel consumption is actually here, so we have data for it, and it's 397 kilograms hour. So it's 397, and that's it. This is the information that you needed for one of the aircraft. And now a little bit more quick, I will fill the information for the rest of the aircraft, because you already learned how to find your information. So for Learjet, we have the takeoff mass 9750, number of passengers 9, empty aircraft mass 5830, 26110 was the mass of the fuel, and information for the wing loading we didn't have. Then the wingspan was 14.58, the wing area was 28.95, the aspect ratio was 7.34, the length of the aircraft was 17.68, and then the diameter of the body was 1.8. Now, the minimum speed I couldn't find, but the maximum was 804. Let me write it here. Then the aircraft has different ranges depending on the passengers on it, but for 8 passengers, okay, I found that it could fly over 3,500 kilometers, actually 3,519 to be exact. Then the maximum height of the flight for 8 passengers were 13 kilometers. The takeoff distance was 1,536, and the landing distance 811. And finally, they also used the Honeywell engine, which was the Honeywell TFE 73120. The aircraft had 2 engines. The thrust was 3114 and 0.32 was the relative thrust. So for Embraer, the takeoff mass was 17,000 kilograms, the number of passengers 12, the empty aircraft mass was the stunning 12,000 kilograms, the fuel mass was 5,900 kilograms, and the wing loading, here I managed to find it, it was 430. Then for the geometry, the wingspan was 20.25, the wing area was 40, the aspect ratio was 10.22, the aircraft length was 20.47, and the fuselage diameter was 1.8. So you can see quite similar values between the different types of aircraft, which is good because our data in that way is validated. Then the minimum speed was 193, the maximum 483, the range of the aircraft was about 5,500 kilometers, the flight height was about 13.7, the takeoff distance was about 1,200, and the landing distance was about 600 meters. Here they also used a Honeywell engine, which was a different type, HTF 7500. They used 2 engines, the thrust was about 6,200 DA newtons, and the takeoff relative thrust was 0.36. I couldn't find the specific fuel consumptions for these engines, so I didn't record them. So now, we simply found an information on the internet, but this is actually quite valuable information, because with it, you can approximate the main parameters of your business jet before starting calculating and re-estimating some of them. So this is your starting point. But I think it's enough for this lecture for today. We recorded all the data, and how we use this data for our business jet, I'm going to talk into the next lecture. Hello guys, in the next few lectures, just before starting to approximate the main characteristics of our aircraft, I wanted just to talk about what we need to pay special attention on when we're doing that. As we already estimated or actually discovered the characteristics of our statistical aircrafts, now we know the current trends in the business jet development. We need to pay attention on in what direction each component of the aircraft are heading. What are the key differences between the data? Where the data is meeting in certain point. So let's say if the range of all the 3 aircrafts that we put it in our statistics is the same, this means that probably our range should be also similar to the one that the 3 previous aircrafts have, or better. Of course, we need always to investigate how we can improve the capabilities of the aircraft that we're designing to be better than the previous ones. We need to pay attention to the maintainability of the aircraft. So this means how to position its components to be easier for the aeronautical staff to maintain it. What is going to be its life expectation? And then once we know this, we can pass this information to the accounting team and they can estimate the potential profits of our project. So a specific components that you need to pay special attention on when investigating your statistical analysis is the aerodynamic scheme of the aircraft, the control surfaces, the power plant, the specific fuel consumption, the flight dynamics, the wing aspect ratio, the maximum takeoff mass, the empty mass, and the wing loading. So all these components we're going to take some average value and to think on how we can use this statistical information to approximate our values. This said, we just need to define the requirements taken from the data we already have and see what are actually these requirements to our specific case in the aircraft, but about this I will talk in the next video. Hello everyone, today we are going to talk about the requirements that we will have to our future aircraft. And the first requirements we are going to talk about are the functional requirements. So these are how many members is going to be the aircraft crew, what is going to be the mechanization for loading and unloading of our aircraft, do we have weapons on our aircraft and where they are going to be positioned, and this is specifically for the military aircrafts. What are the aircraft systems and aggregates? This is not necessarily our job as people that we're going to design this aircraft, but depending on this type, we can just think about it, aware in what direction our project is heading. So, for example, our aircraft is going to be a business jet, we would want to have more aircraft crew per passenger on this flight. Obviously, the mechanization for loading and unloading of transport civil aircraft is pretty much the same for all of them, and they usually have two doors on the front and the rear side of the body of the aircraft. These are pretty much the things that you need to think about before starting designing your cabin and the rest of the components of your project. Then you need to think about the operational components, or what is going to be the exact speed of the flight depending on the engines you've got, what is going to be the height of your flight, the climbing and the descending performance, the range that your aircraft is going to cover, which you have from the project, what is the takeoff and the landing characteristics. Are you going to land on a water, or is your aircraft designed to land on an airport? It depends, of course. In our case, obviously, we're aiming to land always on the airport. And just I want to keep this in mind that not all aircrafts are the transport aircrafts. There are so many different types of aircrafts with different functions and operations. But for us as passengers, the transport aircrafts are just the most popular. And finally, once we figure out what is going to be the structure of our aircraft, then we would like to take a special attention on how it's going to be maintained, what are going to be the fueling procedures, what classes of airports this aircraft can take off and land on. These are very important things that you need to figure out when choosing the parameters for your project. So that was it for today, guys. I just wanted to give you a brief overview for this type of requirements, and in the next lecture we're actually going to choose the main parameters, or the parameters that we're going to start with of our project or of our business jet. Hi everyone, welcome to this lecture, and at that stage we can now start looking for the initial parameters that our aircraft is going to have. To do this, we basically need two things: the table of the three aircraft that we discovered and are similar to ours, and also the requirements for our project. So having the takeoff mass of the three aircrafts, our takeoff mass I would approximate will be about 13,500 for our 12 passengers. Okay, obviously the Embraer Legacy has way more takeoff mass, but it actually covers a higher range than ours. So the Learjet covers similar range to ours, and it has 10,000 kilograms per 9 passengers. Then I would approximate our mass to be 13,500. We have 12 passengers, and this is pretty fine thing. And in that case, I would say that the empty mass comparing to the other aircrafts, so the empty mass of our aircraft could be about 7,900 kilograms. Then the fuel mass, I would say, will be something about 4,000 kilograms. You can see how I'm just approximating all the values, because I know that later on we're going to estimate them more exactly. And the wing loading, because we have only one data for the Embraer Legacy, I would say that in our case we will be less loaded at 308 DAN divided by square meter. Then the wingspan, I would say, is gonna be about 17. The wing area, as our wingspan is 17, then the wing area should be about 34 square meters, which makes an aspect ratio of 8.5. And if you wonder how I found the aspect ratio, it is quite simple. So the aspect ratio usually is equal to the wingspan squared divided by the wing area, which is 34 here. And this is how we're getting 8.5 for the aspect ratio. It's quite simple. Then I would say the length of the aircraft in our case will be about 17 meters, maybe more, but at that point I will put it as 17 because the Learjet aircraft that is quite similar to ours has exactly this type of body length. Then for the fuselage diameter I will just take the average of the three, which is going to be 2.15. And then the maximum speed would be, the minimum speed, sorry, will be about 170. The maximum speed, I would say it's gonna be about 800, okay? And you remember the maximum speed that we couldn't exceed was 950. So this is a valid maximum speed that we're using here. So the range of our aircraft at that point, I will put it at 3000 as stated in our project. Then the maximum height of the flight, I would say it would be about 13 kilometers. Then the takeoff distance, I would say is gonna be about 1500. Okay, let's put 1510. And the landing distance is gonna be about 750, I would say. Okay, and finally, we need to use similar engines as the ones here, because obviously due to these engines and the geometry of the aircraft, then we're getting our flying capabilities fixed. So for this project I will take the Honeywell TFE 73160 from the first project, but here I'm going to use only two of them. So for two engines, the total thrust for this aircraft should be 4448, okay, which is more than enough for 12 passengers, and also the relative thrust in that case will be 0.34, I would say. So that's it, guys. These are all the parameters that we needed to record for our business jet, and once we have this already, we've got, let's say, flavor of what aircraft we're going to build. So we're going to build an aircraft with these parameters that we just recorded. That is going to be a standard scheme of aircraft, so nothing too crazy, and the aircraft is also going to have two engines. So that's it for today, guys. Very good job, you did the statistical analysis. We're done with this section. We're going to look at the mission of the aircraft that is going to complete. I'm going to show the different types of missions. Also, I'm going to be showing you the exact estimations of the masses of this aircraft, the wing loading, and the traction and quality characteristics of the aircraft. So bear with me in the next section, but with this one we're done, and I want to thank you for watching. Hello everyone, welcome to this section, and today we're going to start by defining what is the type of the mission of our aircraft. As I mentioned to you in the previous section, every aircraft or every type of aircraft is having a different type of mission. So the aircraft can be either used for transportation or for civil purposes. The aircraft could also be used for surveillance, for bombing, or for combat. And the last three are usually related to the military aircrafts. So you need to define what is your mission, and depending on the mission you have different stages. You can clearly see the stages of the different types of missions in the figure in front of you. So as you can see, most of the aircrafts, they are civil, and the civil mission is pretty much taking off, climbing, taking a cruise flight, then descending, and finally landing. And these are actually going to be the stages of our mission or of the business jet that we're designing. But I also just wanted to state that in the other types of missions there are also quite interesting segments of them. So let's say for the surveillance you have the surveilling operation, which is a completely different segment from the rest of the mission segments, because there, for the surveillance purposes, the aircraft could hover over a region which also consumes fuel. The same thing for bombing. You need to descend to a certain altitude, then release the bombs, which also is taking a variation in some of the flight parameters. Also for the military flight, you have takeoff, climb and cruise, and then you have the military flight operation, which is a combat with other aircrafts and shooting and so on. So you also need to predict this region of your flight and estimate the fuel and the aircraft qualities for this stage of your flight. As far as we're concerned, our flight is a civil flight, so we would have the takeoff, climb, cruise, descent and landing stage. Okay, so you can state that in your project. So I actually cut the picture of the civil mission and I'm going to place it in our project. So here I will simply drag our mission as this one, and I will just write a statement. The aircraft will be designed the flight stages are takeoff, climb, cruise flight, descent and land. And then I added the picture of our flight mission. So this is all the job, guys, that you needed to do in this video. Thank you very much for watching, and in the next sections we are going to continue with the mass estimation. Hi everyone, before continuing with the mass estimations, I just wanted to state what parameters we are going to look for in this section. So the main aim here is to estimate the takeoff mass by determining each component exactly. So we're going to determine the weight of the fuel, of the crew, of the empty aircraft and so on. And as a starting point we're going to use our statistics, but then we're going to estimate the exact values of the different mass components. Having this, we're going to move on to estimation of the wing parameters, so the wingspan, the thrust of our engines when we're taking off, the qualities of the aircraft and the loading of the wing. And this is quite exciting and it will all be done in this section. Hi guys, I'm very excited today because this is quite an important lecture, because here we are going to see what are the different mass components of your aircraft. So the mass of the aircraft is denoted by M0, and this is the mass of the whole aircraft. And usually in the whole mass of the aircraft we include the mass of the crew, the loading mass, which is the mass of the passengers and their luggage, then the fuel mass, so the fuel that we're using for the flight, and this mass is changing with the flight, and then the empty mass, which is the mass of the aircraft empty or without these components. This is only the mass of the structure of the aircraft. To start our estimations, I actually created an Excel sheet called Project 1 Business Jet, but this time this is an Excel sheet in which I created a variety of tables, and with them we're going to record our parameters and actually estimate them. And as you can see, the first section is called aircraft masses, where we're going to estimate and include all the masses needed for our aircraft. We're going to use this and create tables which we're going to fill here in the next videos. And after that I will add them into the Word project in order to complete it. It's important to mention that we're going to use the Excel sheet not only for the aircraft mass estimations, but also for the rest of the estimations in our project. So here you can see we have section wing loading, then we have the traction and qualities, and I will talk about these coefficients and how we find them in the next videos, but I just want to give you a brief navigation on what we're going to be doing and how we're going to structure our project. Thanks for watching. Hi guys, today we're going to estimate the mass of our empty aircraft. So just a brief overview of what we're going to be doing. We basically are going to use the takeoff mass that is set in our project, or the takeoff mass that we took from the statistical analysis already, and we're going to use it in the equation for the empty airplane mass. And as a matter of fact, in most of the aircrafts, the empty plane mass takes from 0.3 to 0.7 from the whole mass of the aircraft. So the difference is quite big, from 0.3 and 0.7. And for this reason, we're using this equation, which is based actually on experimental data. And we're going to use certain tables and figures in order to determine some of the coefficients. For example, A and C, which are the coefficients from the experimental data that was performed in the past. And also the Kp coefficient, which is the coefficient of the propeller type, is also used in the past studies. So what we are basically doing, we are taking past studies, we're summarizing the information, and with that information, we're basically building the equation that I'm showing in front of you. But enough talking, let's head on to our Word document and I will show you what actually the figures look like. So here you can see the exact section in our Word workbook, okay, and this is an experimental study. And what you can see is the takeoff mass of the flight versus the percentage of the empty aircraft mass. To understand this figure, I will just go a little bit back in our document and show you this section, initial estimations of the aircraft mass. And here you can see the same equation that we saw on the slide, but there is some additional information here. So here we defined two other types of masses, which are relative masses. And don't get confused from these equations, they mean only one thing. So for example, the relative empty mass, which is this one, is equal to the total empty mass divided by the takeoff mass, okay? And this is going to give us a number from 0 to 1, okay? Because the empty mass is always smaller than the mass of the whole aircraft, okay? And from this equation, this determines relatively to the takeoff mass how much is the empty mass. And it's the same for the fuel. Relatively to the mass of the whole aircraft, how much weighs the fuel, okay? And this is, as I said, number from 0 to 1. Obviously it will never be 1 because the aircraft cannot be only fuel or only empty, okay? And as you can see, here the whole equation can be modified. Or what we're doing, we're multiplying the takeoff mass, we're multiplying it by, let's say, the relative empty mass. And in that way, we're getting the total empty mass, okay, which is the same as MEY, okay. So MEY divided by M0 multiplied by M0 will give us MEY, okay. And in this way, we're distinguishing the relative components from the exact components. I hope this is clear. If not, you can ask in the questions below. But anyways, since I explained this already, now we can look at the figures. Well, I would say it's very hard to find the exact value on this chart. And you can see that here, these lines, they represent different types of aircrafts. For example, this is a jet fighter, this is a jet transport aircraft, this line here, okay? And on these lines, you can take points depending on the takeoff mass and find what percentage of the takeoff mass is the empty mass, okay? For example, here it will be about 50%. So let's say if we have a jet transport aircraft that have total takeoff mass of 50,000 kilograms, then this means that its percentage or its empty mass will be about 0.5% or 25,000 kilograms in total. Okay, so based on this figure here, we're defining the A and the C coefficients, and they are taken exactly from this chart here. So the equation that you can see here is basically based to this chart. And in order to transform this chart into equation, we're using these coefficients A and C. And in our case, the A and the C coefficients will be taken for jet engined aircraft, okay? Since we have a business jet, it is going to be powered by jet engine, which is going to be Honeywell, as you saw in the previous videos. So we're going to take A equal to 1.59 and C equal to minus 0.1. Let's apply these coefficients. I will actually create one more table here, and here I will write A and then I will write C, okay? So the value of A, as we said, is 1.59 and the value of C will be minus 0.1. Okay, and actually I'm gonna upload this Excel sheet for your simplicity. I'm gonna import an empty version which you can use for fill once you're completing the project, and also I will upload a complete version so you can see the formulas that I will apply and the values that we are going to get. And I actually added one more tab, the relative empty mass here, because we will need it. Okay, so the starting point, as you saw from the presentation, and I'm actually going to show the formula here now. So we are taking the takeoff mass from the statistics. So from the statistics, we estimated that our takeoff mass should be around 13,500, right? And you can actually see it here. This is from our project. So we use this value 13,500. And then, since we have our takeoff mass, we want to estimate the empty mass. So as the coefficient K is usually 1 for fixed propellers, this means that we're not going to change it, and actually we can neglect it here because it's equal to 1. So I will not add it in that equation. So let's actually write it. Let's write here equal, so the MEY star is equal to A multiplied by bracket 2.2 multiplied by M0, so select here M0, and then this will be to the power, so what is in the brackets will be to the power of C, which is minus 0.1. Okay, that's it. And we're getting the value of 0.56 and more numbers. Okay, so this is the relative empty mass, or the empty mass of our aircraft will be about 50% of the total mass of the aircraft. So now we can actually estimate the mass of the aircraft that is empty. And this will be quite simple. We just need to multiply, so as we have in the equation here. So from the equation here, we're having the MEY star and we're having M0. So MEY, or the empty mass, will be equal to EY star, or 0.56, multiplied by the takeoff mass, or 13,500. And this is what I will do. So this will be equal to 13,500 multiplied by the relative empty mass. I will press equal, and we're getting that the empty mass of our aircraft will be equal to 7,663.996 exactly. So that's it, guys. Now we have our empty mass. I'm not yet going to update our project because this table is not ready yet, but that was the empty mass of the aircraft, and in the next lecture we're going to estimate the rest of the masses. Thanks for watching. Hi guys, today we have quite an easy task comparing to the previous one. We need to estimate the mass of the cabin crew and the mass of the passengers and the loading. So the normal standard for aircraft that has 12 passengers for cabin crew is to have at least one flight attendant. And this is what we're going to be doing. So we're going to assume that our aircraft will have one flight attendant, and also every aircraft should have at least two pilots, especially the transport one that are transporting people from some point to another. So our crew will be built from two pilots and one flight attendant. Then let's talk about the passengers. So we know that our aircraft should have maximum 12 passengers, and this is how we're estimating their weight. So we usually assume that every passenger is about 90 kilograms, which is overestimation of the weight, but it is better to have overestimation than underestimation. And we also add some value for the baggage that each passenger is having. Okay, and actually we're usually using two approaches, or estimating the luggage per passenger, or we're taking the volume of the baggage area and multiply it by 180. You can use either approach for estimating the baggage that will be inside the aircraft. But let's head on to the Excel sheet and estimate these types of masses. And I'm actually going to use the second approach for the luggage, and we're going to assume that each passenger is having about 30 kilograms of luggage with himself. So the cabin crew mass from the equation here will be equal to 90 multiplied by the number of cabin crew members. And I will actually be more optimistic and I will make it 8 here. So this will be equal to 80 multiplied by 3. Actually, I'm going to use 90 here. So 90 multiplied by 3, and we're getting 270 kilograms for the weight of the cabin crew. Then for the passengers, okay, here I will assume that each passenger is about 8 kilograms. And then I will multiply that by the number of passengers, which is 12. And I'll also add 30 kilograms for the baggage of each passenger multiplied by the number of passengers, which is 12 again. Let me put the equal sign. And we're getting that the total loading mass is about 1320 kilograms. Then let's estimate what is going to be the initial mass of the fuel that we have left, and once we determine how much fuel we have, then we're going to move on to the fuel mass stage, where I will estimate the fuel mass for each stage of our flight. So here this will be equal to the total mass of the aircraft minus, and actually I'm just wanna share the equation that I use here. So once in this equation we have the zero mass, we have the cabin crew mass, we have the loading mass, and we have the empty mass, we can restructure this equation and simply find the fuel mass. Okay, so m0, or the takeoff mass, minus the empty mass, then I will do minus the crew mass and minus the loading mass. And you can see that we have left 4,246 kilograms of fuel that we can take on this aircraft. This is the maximum fuel that we can take. And that was everything, guys. So now I will add this table inside our project. So here in the initial estimates for the aircraft mass, I will add this table here, okay, and I will just center it. And these are going to be the initial estimates for our masses on the aircraft. Okay, and then we can move on to the estimated mass of the cabin crew, and here I will simply write that it is equal to 270. Then the loading mass is going to be equal to 1320, and the empty mass, I'm going to add here the empty mass. So the empty mass will be equal to 7664. This is going to be in kilograms. And actually the rest of the masses I'm also going to add kilograms, just to be certain. That's it. So guys, we are ready with the basics of the masses, and bear with me in the next section where I will estimate the mass of the fuel for each stage of the flight. Thanks for watching. Hi everyone, welcome back. Today we are going to talk about how we can estimate the fuel mass for each segment of your flight. And the segments of your project are takeoff, climbing, cruise flight, descending, and landing, which are 5 segments, okay? You should remember that, because the relative mass of the fuel is estimated when we have the weight of the aircraft in every next segment. So if we have the starting point as taking off and we know how much fuel we used for taking off, then we will know how much fuel we have left for climbing. And if we know the percentage of the fuel that we need to spend for climbing, then we can estimate this fuel. And once we estimate the new weight of the aircraft, we can estimate the fuel for cruise flight, for descending, and for landing. And this is what this equation here is representing. So M1, M2, M3, and Mn are basically representing the segments. So this is segment 1, which is takeoff, then segment 2 is climbing, then segment 3 is cruise flight, and so on, until we reach our last segment. And actually here it should be I, but I put N instead, so sorry for this mistake, but it doesn't change the logic of this equation. And if you don't understand this, don't worry, I'm gonna show you how you do exactly that on practice. And as I said, here we're going to estimate our fuel for the takeoff, climb, cruise flight as well. And as the fuel usually used for descending and for landing is not that much, we're actually not going to estimate it here, but we're also going to add the aeronavigational reserve, which every aircraft should have just in case of emergency. Okay, so here we are in our workbook, and you can see that the first thing we can estimate is the takeoff fuel segment. So what we have here is that usually the fuel takeoff segment have a relative mass of 0.97, or 0.97% of the fuel is left after you complete this segment. Okay, so this means that for the takeoff segment we have 0.97 as our fuel ratio. And then also the previous segment, so the previous segment before the aircraft takeoff, is when the aircraft have its full mass and the full fuel tank. Okay, so this will be the full mass of the aircraft. So mi minus 1 should be the previous flight segment. So here we have the full mass of the flight, because before the takeoff the aircraft haven't performed any action, so all the weight is on the aircraft in the segment before the takeoff, if it makes sense for you. So now here we can estimate this segment, the takeoff segment, by the following equation. So the fuel that is left after the takeoff, or actually not the fuel, the mass of the aircraft that is going to be left after we take off, is going to be 13,500 multiplied by 0.97. Okay, so after our takeoff segment, the mass of the aircraft will reduce with 400 kilograms. So imagine how much kilograms of fuel are consumed just for taking off. Then let's move on for our climbing stage. So at the beginning of the climbing stage, we have our fuel to be equal to 13,095. Sorry, not the fuel, but the weight of the aircraft. So in the beginning of the climb stage, we have 13,095 kilograms of aircraft weight. And then here, as you can see in the workbook, the fuel in that stage is determined by this equation, and we need to add it. We need to add it here. Okay, but before that, we need to define the DH, which is the required climbing altitude, which I'm gonna put at 10 kilometers in the beginning of the cruise flight. And then we can start writing the equation in the cell in front of the mass ratio in the segments area. So this is going to be equal to bracket 1 minus 0.009 multiplied by DH, which is equal to 10 kilometers in the C system. And this is going to be divided by 1 minus 0.0045 multiplied by the climbing altitude. So let's select this again, let's close the bracket, and we're ready. So we're getting this number that during the climb stage we're going to reduce the weight by 0.9528 and so on. So finally, the weight of the aircraft after the climbing segment will be equal to 13,095 multiplied by the climbing coefficient for the fuel burn. And then we're getting that after the climbing segment, we're going to have mass of the aircraft equal to 12,477 kilograms. Then I'll estimate the mass reduction for the cruise flight, which obviously is going to be the most major reduction, as we use most of the fuel in the cruise flight, because this is the longest segment to overfly. And here you can see that you have exponential, but don't worry about this. I mean, you can simply use the Excel features in order to calculate that. But first, let me record here. So this field will be equal to this one. So in the beginning of the cruise segment, we're going to have this weight of the aircraft. And here, the coefficient will be equal to EXP. And you can see here EXP, just selected. And then it takes a number. So let's write inside bracket minus L, and I'm gonna write L just in a second. Let's first select it here, because we're going to use L here. Multiplied by C. Let's close the bracket, and this will divide it. So the L is the flight range, and the C is the specific fuel consumption of the engine, which we already took from our statistical analysis for the engines that we are actually going to be using. So we divide this by the cruise speed, which I'm going to put here, multiplied by the aerodynamic quality coefficient. which is equal to K. And usually the quality coefficient you can find, I'll keep that. So usually the quality coefficient for this type of aircraft, you can find it in internet quite easily. It is usually equal to about 16. So here I will put 16 as a quality coefficient. Then the velocity, let's see what cruise velocity we chose for the aircraft. So the maximum speed we chose to be 800. So I would say the cruise speed is going to be 780. C is the specific fuel consumption, which is 1.9, and L is the flight range, which in our case is 3000 kilometers. Okay, so finally, having all these values here, we estimated that for 3000 kilometers, our cruise fuel coefficient will be 0.63. So finally, the fuel after the stage will be equal to 12,477 multiplied by 0.633, and we're getting for our mass after the cruise flight to be equal to 7,902. Okay, and then the final stage is our aeronavigational reserve. So usually the aeronavigational reserve is 3 to 5% of the total mass of the flight. So if we make it to be 3%, so I will make it 0.97 of the total mass at that segment, and then here this will be equal to 7,902, and finally we will find the final mass of our aircraft to be equal to 7,902 multiplied by 0.97, which is going to be equal to 7665. I will actually remove the last two lines because they're left from the previous table, and let's investigate a little bit what are our results here. So what we're seeing here is that once the aircraft lands, it should have a mass of 7,665 kilograms, right? So this should be the mass of the empty aircraft plus the loading mass plus the crew. Okay, and our initial estimations show that the empty mass only is 7,663 kilograms. And if we actually deduct from 13,900, we deduct 7,665, we find that the fuel that we actually are going to need is about 5,800 kilograms. And our initial estimations showed that the fuel we need is 4,000 kilograms, and this was based on the statistics. Okay, and what this means is that we will need to increase the mass of our aircraft in order to ensure that we can utilize this additional fuel and also take all the passengers that we need that are going to weigh about 1,500 kilograms. Okay, so that was everything for today, guys. The final mass we're going to use for our aircraft, the takeoff mass, is going to be changed to 15,000 kilograms. So I'll actually add this table here so we have a record of it. Okay, here we go. Let's place it in the middle like this, and I will also add all the coefficients that we used in our estimations as well. So here we go, guys. Bear with me to the next sections where we're going to estimate the wing loading and the traction and the qualities of the designed aircraft. Thanks for watching. Hi everyone, welcome back to this section, and today we're going to estimate the wing loading. Usually in aviation, there are some situations in which we want to estimate some coefficients for the worst case scenarios possible, and then take the most unbeneficial coefficient in order to be sure that our aircraft covers all the situations out there that could affect it. And this is what we are going to do today. So today we are going to estimate the loading coefficient for three different scenarios. The first one is the landing condition. So when the aircraft lands, then we're going to estimate the same coefficient, but for cruise flight or for the ability of the aircraft to maintain a cruise flight. And finally, we're going to estimate the loading coefficient in the other difficult situation for the aircraft, or when the aircraft is maneuvering, which means when the aircraft is changing fast its speed or direction. So we want to ensure that we have enough strong structure of the wing in order to cover all these situations, and this is what we're going to be doing. And then after we found the three coefficients for each of the situations, then we're going to take the minimum one, which refers to the highest loading on our wing. And here we are with our workbook, and you can see all the equations here that are for each situation. So the first we have equation for the landing conditions, then we have equation for the cruise flight, and finally we're having an equation for the maneuvering conditions. And also you can see this section here in our Excel worksheet, which is called wing loading, and here I will first record all the necessary parameters in order to estimate the loading coefficients, and finally we're going to actually estimate them here in these columns and take the minimum one. So let's not lose any more time and let's start it. The first coefficient is the landing coefficient. And to estimate it, you first need the sea length Y max, which is the lift coefficient while landing. And normally this coefficient, I will tell you how much it is. It's about 3 for the standard aircrafts. Then the minimum velocity, you can check it from your table, from the statistical analysis that you choose for your aircraft, and it's about 170 kilometers per hour. Or if we estimate this in meters per second, because obviously we want to use the speed or the velocity in meters per second, I will actually show you one very simple way to do it. So if you have 170 kilometers per hour, you simply need to multiply it by 0.277, and this will be equal to 47.09 or 47.1. So let's write this for the minimum velocity, 47.1, and I will just write here meters per second so you're aware of that. Now, since we have the minimum velocity, then it's time to determine the relative horizontal flight fuel mass, okay? And this is usually equal to 1 minus the cruise flight segment, okay? Because this is the horizontal flight when we're at cruise level. So what I'm going to be doing here is I will simply write 1 minus, as you can see here, 1 minus this segment. So it is this one, and this will be equal to 0.366. Then the last thing, actually there is nothing left, and now we can estimate the loading coefficient for the landing condition. So this is P1, and P1 will be equal to Cy max length, but first I write a bracket. So Cy max length multiplied by bracket V min, which is 47.1, multiplied by 1.3, and I will square this, okay? Then I will close this whole bracket and divide it by 30, by bracket 30.2, multiplied by bracket 1 minus the relative fuel mass at the cruise level, and then let's write two brackets, and we're ready. So we're getting 588 for the loading coefficient, which is the having the dimension of dA Newton divided by meter, okay? And since we have this one, now we can move on. So the loading coefficient for the cruise flight is equal to the Cy cruise, or the lift coefficient during the lift flight, during cruise flight. So usually the lift coefficient while the flight is at cruise speed is very small, and this is because a flight to maintain a horizontal level, this means that the lift should be neglected from the weight, because if the lift is too high, then the aircraft will be climbing, but this is not what we want a cruise flight. So normally at cruise level the lift coefficient will be about 0.53. So for example, the lift coefficient during cruise flight for A320, it's about 0.566. So between 0.5 and 0.6 is a normal lift coefficient during a horizontal flight. Then what you need to determine is the density at the altitude that we're flying on, and usually our flight is going to fly at about 10,000 meters. So you can simply check in Google what is the air density for 10,000 meters. So you can see here that in C units at 10,000 meters we're having the density about 0.41. okay, so this is the value that we're going to be using. So let's write here 0.41. I will actually write it a little bit lower because our aircraft is going to aim a flight between 10 and 12,000 meters. So instead of 0.41, I'll write it 0.31 in order for us to really have the maximum loading condition. So I write it 0.31 here. So let's do this. And that's it, guys. We have everything actually that we need for this equation. So here in P2, let's write. So this is going to be equal to CY cruise flight multiplied by the air density multiplied by the cruise velocity. Actually, I didn't write the cruise velocity, but I will write it in a second. Let's close the bracket, and here this is going to be divided by 20 multiplied by 1 minus 0.6 multiplied by the relative fuel consumption at horizontal flight, which is 0.366. And that's it, guys. Let's close the brackets here, both of them. And for now we are getting 0, but now we're going to estimate the cruise velocity here. So as you remember, our cruise velocity was 780, and this is what we're going to be using. So 780 multiplied by 0.277, and this will give us 216.06 meters per second. So let's write this 216. I will round it to 0.1 actually. So we're getting an error here, and I mean this is an impossible value, and this is because I didn't square the velocity. So let's do that. So here I will simply write squared, and now we're getting more logical number, which is 491, okay, dA Newton per meter squared, okay. So that's it for the second one. For now, the cruise condition has lower coefficient, so we're going to take that for now. But let's see the maneuvering overload. So a typical lift coefficient for maneuvering is going to be about 2, and also here we will need to have the overloading coefficient. So 1 means that we want to ensure that in real conditions we're protected from the standard overload. But what we want is the aircraft to be able to handle way more overload than it will actually ever happen in the real conditions. So for that reason, the overloading coefficient is usually taken with 50% advance or 1.5. And finally, we will need to estimate the dynamic pressure, okay? So the dynamic pressure is estimated actually quite simple. So the dynamic pressure, this is the pressure that is made from the velocity. So it's related to the velocity at that altitude, so to the maximum velocity. And I will show you how much it is. So it is usually equal to the density at certain altitude. Actually, I'll write a bracket here. So the density at certain altitude multiplied by the squared velocity, okay, and this is going to be divided by 2. This is the dynamic pressure at certain altitude with certain speed. And we're getting 7,238 for the dynamic pressure. And now we're ready to estimate the maneuvering overload of our aircraft. So this will be equal to 0.1 multiplied by CY maneuvering, so this one, divided by the overloading coefficient. Let's close the bracket, and this will be multiplied by the dynamic pressure that the aircraft experiences while maneuvering. That's it. And this is going to be equal to 965 dA Newton per meter squared, which is very high, so this means that we're not going to get so much overloading in that case. And obviously here the cruise flight overload is the most significant, so this is the value we're going to take. And I will just mark it in yellow so you can recognize which value we're choosing for the overloading. So that was, guys, everything for today. I will just put the table here and we're ready for today. So let's add the table in our project. Here we go, let's put it in the middle, and we're ready. We took this overload, and I would then simply do the answer of our equations. So the landing overload was equal to 588 d Newton per meter squared. Okay, that's it. Let me just make it look nicer. That's it. Then for the cruise condition, we got 491.8, and finally for the maneuvering condition we've got 965 actually. So this will be equal to 965. That's it. So we're ready, guys, with this section. The project is updated and we have our results, so there is nothing left to do for today, and I will see you in the next section when we're going to talk about the traction and the qualities of the aircraft. Thanks for watching. Hello everyone, welcome in this lecture, and today we're going to be talking about the aircraft quality and the traction. So, or this means the ability of the aircraft to have enough thrust in order to overtake certain tasks while flying. So again, here we're going to take the three cases where the aircraft requires the most lift and qualities, and then take in this time the highest coefficient needed in order our aircraft to complete these tasks. So obviously one of the most difficult situations that we want to ensure that the aircraft takes control on is when we have failure of one of the engines. So we are going to check that, and the first condition is the aircraft to be able with its thrust of a single engine to perform a standard flight. Then the next condition will be our aircraft to have a proper cruise flight with a thrust that is requiring, so it can maintain its normal cruise speed with the thrust that the engines provide. And finally, we want to ensure that our aircraft takes off from the distance that we mentioned in our estimates. So you remember, we're normally having a standard takeoff and landing distances that we want to ensure that the aircraft meets in order when it takes off from a runway not to go out of it before even took off. Okay, so we want to ensure this as well. And let's head on to our workbook and to our Excel sheet where we're going to estimate these parameters. So here we are, guys, in our workbook, and you can see all the equations needed for you to estimate these coefficients. I just need to put a star here and let's talk about it. So here we have all the parameters, okay, that are going to be used in the equations, and then below what you have is the exact coefficients that you will need to estimate. Okay, so now let's check the first equation, and for the first equation we need a KV, which is a coefficient, and I actually didn't write his value here, but it is equal to 1.5. okay, so here this is equal to 1.5, and then so the KV is a climb coefficient. I just need to mention that. Then the aerodynamic quality when the aircraft is taking off is usually about 10. So actually I didn't mention what means aerodynamic quality, and this is usually the lift divided by the drag on the aircraft, and this is giving you the total quality. And usually a positive quality means that the aircraft is actually climbing and the lift there is active. So for climbing we have the aerodynamic quality of 10. Then our number of engines is 2 because we chose this number of engines. Then the climbing gradient, so then we need to find the climbing gradient, and usually it is equal to 0.017. This is standard climbing gradient. Then the cruise flight density will be equal to 0.31. okay, then the takeoff lift we're actually going to estimate a bit later, because now I think we can estimate the climbing with one engine failed, and we can estimate also the horizontal flight traction coefficient qualities. So let's see the first equation. So this is equal to 1.5 multiplied by the number of engines, which is 2, divided by, again, the number of engines, which is 2, minus 1, okay? And this is showing how our aircraft is actually going to behave when one engine is off. So this is going to be multiplied to 1 divided by the climbing quality, which is this one, or equal to 10, plus the climbing gradient, which is 0.017. Let's close a bracket here. Okay, I needed to close one more bracket, but Excel will close it instead of me. So let's select OK here. And here you can see that for failure engine, you get the traction coefficient equal to 0.351. Let's estimate the same coefficient, but for maintaining a horizontal flight. This is going to be equal to 1 divided by K. So 1 divided by the quality at cruise flight, which we have actually here, and it's 16, multiplied by the density at cruise flight. I actually wrote another letter from the one that is defined here, but this actually doesn't matter. So let's multiply this by 0.31 to the 0.85, and then multiply this to 0.8, which is the throttling coefficient. Okay, and we're getting 0.0211, okay, for the cruise condition. So for now we're going to take the engine failure condition, because we have higher coefficient here, and as you remember, we're taking the highest coefficient from all our estimations. But let's see how we're doing with the takeoff condition. So the takeoff lift, we will take it the maximum to be equal to 2.3. Then we need to determine the friction coefficient on the landing gear, okay, when we take off. So you can see the different friction coefficients here for the different types of surfaces. And obviously we need to take the worst one, which is on snow and ice, okay. So we have it equal to 0.02. And this is the value I will be recording, 0.02. Okay, then the distance for taking off, it's actually equal to the, actually we have it from our statistics, and I will check it right now. So the takeoff distance here is equal to 1510, so 1510. And then for the quality when taking off, we will write 12, because it's equal at about 12 for the standard aircrafts. So that's it, guys. We can now estimate finally the last traction and qualities coefficient, and this will be equal to 1.05 multiplied by 520 divided by bracket CY max takeoff multiplied by the takeoff distance in meters plus 0.5 multiplied by 3 multiplied by the friction coefficient plus 1 divided by the quality when taking off. Okay, that's it. And again, I missed one bracket, but Excel will cover this. So the takeoff coefficient when taking off, so the takeoff condition, will be equal to 0.23. And obviously here you can see that actually this really makes sense, that when we have one engine off or we have engine failure, we have the traction coefficient which is the highest. So we're going to take this one as in our estimate, and it really makes sense because the worst qualities of the aircraft we will have when we are losing thrust directly or when we don't have one engine. So let's copy this, and I'll paste it just below this section, and let me just place it in the middle so it looks more representative. There we go. And I will just write the values for each coefficient here, as we always do. So this one is equal to 0.351. Then the horizontal flight coefficient is 0. Actually here I think there is an error because this one is too small. Let's see what there is. Yeah, so here I multiplied by 8, but I had to multiply it by 0.8. Okay, so 0.8. And yeah, now the coefficient is quite normal, because here obviously the throttling coefficient is 0.8 but not 8. And okay, so this one is 0.21. We wouldn't do a big mistake because we would still take the engine failure coefficient. So 0.211. Okay, this one was for the previous. So this one is 0.211, and the last one will be equal to 0.232. And that's it, guys. We're ready with this section. We took the engine failure traction coefficient that we're going to be using further in this project for the next estimations. That was actually the end of this section. I want to really thank you for solving all these equations, and I will see you in the next section. Hi everyone, welcome back to the course. In this section, we're actually going to choose the parameters of our wing and also the control surfaces. But before that, let's just talk about what is wing, what are control surfaces, and how they're used in order to build an aircraft. So the surfaces on the aircraft, they can be either control surfaces or the one that produce lift. So obviously, for the most common types of aircrafts, the surface that produce lift is the wing. There are surfaces for stabilization, which are called the vertical and the horizontal stabilizers, and we need to design them. Also, there are surfaces that control the flight, which are called control surfaces, and these are the rudder and the elevator, and they control the direction in which the aircraft is going to be heading, and also they are used for the balancing characteristics of the aircraft. So depending on how these type of surfaces are positioned on the aircraft, we have a few schemes that we need to choose from when we design our aircraft. And the first scheme, this is the standard scheme, which means that the wing is in front of the control surfaces and the control surfaces are placed on the same location, which is called the tail of our aircraft. We have a flying wing scheme where we use a single surface, that is a wing, and this surface have two functions. It both produces lift and at the same time is used for controlling the flight. And finally, we have the four-plane scheme in which the stabilizers and the control surfaces are in front of the wing. Okay, so the wing and the lift production is behind the stabilization surfaces. So these are all the schemes that we will need to choose from when creating an aircraft, and in the next section we're actually going to do it for our certain type of aircraft. So thanks for watching, and I will see you in the next lecture. Hi everyone, welcome back to this section, and today we are going to choose the scheme of our aircraft. And usually we're choosing the scheme depending on what is the function of our aircraft. So if it is a military one, maybe we would like to choose flying wing, let's say. There are also military aircrafts with all different types of schemes. Actually there you can improvise with the scheme that you choose. However, in our case we're creating a business jet, so here the things are pretty straightforward. So before doing that, we need to pay a special attention to some of the following criteria in order to decide what is going to be our scheme. And the first criteria, which is very important, is the positioning on the crew and the load on the aircraft. Then we need to decide what type of mechanization we're going to use for takeoff and landing. Also, where we would like to position the engines. Are they going to be positioned inside our wing or are they going to be positioned in the tail? There are also aircrafts that have their engines positioned in their front section. So there are quite many different types of positions we can choose. Also, if we have a military aircraft where we would like to position some of the weapons and of the armory that is going to be on this aircraft. But let's head on now to the workbook and to the Excel file where I prepared for you a table from which you can choose your scheme and the main components of your aircraft, based on which we're going to do our estimations later on. So here I have open on one side the workbook and on the other side the Excel sheet that we're working on. So as you can see in the workbook, we have a table, and in this table are basically all the components that we will need to use in order to determine how our aircraft is going to look like. And the first we will need to choose the aerodynamic scheme. So from this table I'm going to choose certain parts for our aircraft, and then I will record them in the table inside the Excel. Then we're gonna import the table from the Excel inside our Word document, so our project is completed. So firstly, the aerodynamic scheme that I'm going to choose actually is the standard. So I choose a standard scheme. Then for the position of the wing, as most of the business jets and of the aircraft have low wing positioning, I will add it here. And usually all the transport aircrafts are having low positioned wing, and this is because if they land in a water, the fuselage is above the wing, so the passengers are not under the water. This is very important to know. Then our wing shape is going to be trapezoidal, and these components usually you can research in internet for other types of aircraft that are similar to yours, what components they use. This is how I choose this information right now. So here we also have the wing sweep, and I would like a standard wing sweep. So this is how much the wing is swept. And if you don't know what is wing sweep, I advise you, and if you're interested in this, to take a look at my aerodynamics course, where all the components of the wing and all the designs of the wing are explained. Then the control surfaces, I will use the T-shape, which is also quite common. Basically for civil aircrafts, you either use the standard, which are engines inside the wings, or the T-shape. The both schemes are proven to be very common for this type of aircrafts. Then the cabin shape is going to be circular. Then the landing gear, there are today no many aircraft that are having tail wheel, and I will explain why in a second. So we're going to use a front wheel. So we usually don't use tail wheel because there is one effect when the aircraft lands and the wheel is on the back. So one of the wheels is on the back. This means that when the aircraft lands, then a lift can be produced from the wing. Okay, and once the lift is produced from the wing, we're creating something like a bouncing effect from the ground, and this is not happening when the wheel is positioned on the front of the aircraft. Very important to know. Then the engine type is turboprop. So this is a standard turbojet engine. Also there are aircrafts with turbofan. So turbofan, and also there are aircrafts with turboprop engine, which is actually an engine with a propeller, but it's still a jet engine. So the force is produced from jet engine, but this is then converted in order to rotate the propeller. But what we're going to use here is a simple turbofan engine used for most of the aircrafts. And then the number of engines, we already choose it. We'll have 2 engines. And finally, the position of the engines is going to be in the tail. Okay, as I told you, we have basically 2 schemes for the commercial aircrafts. Either we can position on the tail or we can position on the wings, the engines. And these schemes prove to be very sufficient for these types of aircraft, so we cannot neglect that. So that was it, guys, for today. We're actually done with recording the main parameters of the aircraft, and in the next lecture we're going to continue with estimating the airfoil and the geometry basically of the wing. So thanks for watching, and I will see you in the next. Hi everyone, today we're actually going to design our wing. So we're going to estimate all the main components and parameters we need in order the wing to be able to be built from the manufacturers. Okay, so our design for the wing today will be ready. But I first want to take a look at some many important parameters of our wing, and I actually downloaded this scheme from NASA, so it's quite relevant. Just for you to see some main components of the wing. So the first thing is that the main components that design a wing are the wing area, which is measured in meters squared and is basically the whole area of our wing. Then we have the wingspan, which is basically the length from wing to wing, from side to side. Okay, then we have our chord, and the chord is the distance from the trailing cage to the leading cage. And remember, since our wing is trapezoidal, this means that our chords are not going to be the same on the wing tip and on the wing core. Okay, so this is very important to measure, and because of that our estimations will be a little bit more difficult. But since most of the today's aircraft have trapezoidal wings, it is worth it to estimate this a little bit more complicated, but to have relevant knowledge to what has been done in the industry today. Also, some quite important coefficients for the wing is the aspect ratio, which is basically the squared wingspan divided by the wing area. And for the wings that are trapezoidal and they have different type of chords, we also have something called taper ratio, which is basically the ratio of the core chord and the rear chord of the wing, and we're also going to be estimating that. I just want to mention that the coefficients used from NASA are going to have different names than the coefficients we're going to use in our project. For example, for the wingspan we're going to use L, and for the wing area we're going to use A, while for the chords we're going to use B. But you will see this just in a moment. Okay guys, here we are now in our workbook and also in our Excel sheet for the project one, and I actually downloaded a picture of a very similar business jet to the one that we're going to use. So it has the engines inside its tail, and also the size quite matches our size, so this is quite good. And I will use this in order to show you graphically some of the coefficients we are going to be estimating. So first, you remember the traction and the loading coefficients we were estimating last time. Remember them. So we choose basically the engine failure traction coefficient of 0.351, and we also choose the cruise loading of 491. Now we can use these coefficients in order to estimate the desired wing area and the desired thrust. Okay, so this is what I'm going to be doing. So this will be equal to 0.1, actually bracket 0.1 multiplied by the M0, or the mass of the wing. So at first the mass was 13,500, and then we added 1,500 because we underestimated the mass, if you remember. So this is our total mass, and actually this is going to also be in the brackets. So basically we're multiplying 0.1 to our total mass of the aircraft, and now the whole this thing I will divide it to P0, and the P0 is our wing loading coefficient. Okay, so it's 491. So I will divide this to 491, and actually notice that in this equation I missed something. Well, you will have it now in your workbook, but this is G. So this is the natural earth acceleration, which is always equal to 9.81. So I will just need to add it here. So this will be multiplied to 9.81, and here we are getting the wing area about 30 squared meters. Okay, so this is meter squared. Then, since we have the area of our wing, now we can estimate the desired thrust. So remember we assumed, and I think this was in our statistical analysis. So if I go, we were estimating basically the value based on statistical analysis, but now we're going to change that value, okay, of the thrust needed for the aircraft, and we will see if we would need to change the engines that we chose on the first place. Okay, so this will be equal here to 0.1 multiplied by the P star 0, which was our traction coefficient. So it is this one here. Okay, and this will be multiplied to bracket, and again here 13,500 plus 1,500. That's it, and again this will be multiplied to the 9.81, which is the earth acceleration. That's it. So as you can see here, we need a little bit more thrust than our engines can provide. So what we estimated firstly was that we will need two engines, and this was purely because of the statistics. We estimated we will need 4,448 newtons of thrust, okay, but now we can see that we will actually need 5,164 newtons of thrust. And this makes sense, right? Because since we increased our weight and we completed some of the estimations, now we know more about the aircraft with every next step. So we need to choose other engines. And I actually found the engines, you can also research them. But I found more powerful engine, which is Honeywell F124 J100, which produces, so two of these engines will produce 5,220 DA newtons, and also their relative thrust in 0.36, which is now acceptable for our needs. So we're going to change the engines to these ones. And this is normal when you are designing an aircraft, to constantly change with every next step the variables of this aircraft. The next thing we'll definitely be sure about from our statistical analysis is basically the aspect ratio of our wing. And you remember the aspect ratio was the squared span divided by the surface of our wing, or the wing area. So let's take it as 8.5. And then since we know the span of our wing and we know the aspect ratio, now we can since we know the wing area and we know the aspect ratio, now we can find the wingspan. And this will be equal to square root, and this in Excel is SQRT, and then multiplication between the S and the aspect ratio. That's it. So the length of our wing will be about 16 meters. Okay, so this value is in meters. Then the taper ratio, as I said, is basically the ratio between the inner chord and the outer chord. You can see now here from this drawing that they are different. And normally, in most of the cases, the taper ratio is about 3. So usually the inner chord is 3 times the outer chord. So this is going to be the ratio that we're also going to use for our project. Okay, so now we need to find the chords. And what we know for now is that the inner chord is 3 times, okay, or the taper ratio, so this will be equal to the taper ratio multiplied by the outer chord, okay. So this is the ratio between them. But how are we gonna find the outer chord? Well, here it's a little bit tricky, but I will explain in the best way. So as you can see, we can find this by using the medium geometric chord, or this is our chord in the geometric middle of our wing, okay. And as you can see, it is equal to the inner multiplied by the outer chord divided by 2, and this is equal to the S divided by L. So we know S and we know L, so we can actually estimate the median geometric chord, and this will be equal to S divided by L. So now we have our median chord. And since we have it, we can find another ratio for the B0 and BR and basically estimate it as a system of equations. I will actually draw this for you. So what this basically means is that if we have these two equations, so let's say that B0 is equal 3 times BR, right? And this is one of the equations. But at the same time, from the medium chord, and we know how much it is, and we know that it is actually 1.876, so here we have 2 multiplied by 1.876, okay, will be equal to B0 multiplied by BR, right? But we know that already B0 is equal to 3 times BR, right? So we can actually swap this here. Okay, so then what we will have from this equation will be 2 multiplied by 1.876 will be equal to 3 times BR multiplied by BR, which is actually 4 times BR, okay? Or this will be equal to 1.876 will be equal to 2 times BR, okay? Because we reduce this one by 2 because of that symbol here, okay? And actually we can use that equation for finding the BR based on our median geometric chord. And this one here, 1.876, is actually our BM, okay, or the median chord. So what we found here is that BR is 2 times smaller than the median chord, and this is what I will write here. So basically BR will be equal to the median chord divided by 2, okay. And now you can find that the outer chord or the rear chord is equal to the 0.93, while the inner chord is equal to 2.81, and this is how you find the chords based on the median chord. So now, since we have all these chords, now we can find the median aerodynamic chord. And you might get confused what a median aerodynamic chord is. So the main difference between the geometric and the median aerodynamic chord is that the geometric is based on the dimensions of the wing, okay, while the aerodynamic is based on the forces that are applied on the wing. So let's say on the aerodynamic center or on the aerodynamic chord will be applied the lift that the wing produces, and this is not necessarily at the same point where the geometric chord is located. So this is important to know. That's why we have different equations, and we need to provide to the constructors both the position of the geometric and of the aerodynamic chord, so they are sure that once they build the aircraft and they test it, all these chords are on the right position and the aircraft flies properly. So for the median aerodynamic chord, we have 2/3, so bracket 2 divided by 3, and then this will be multiplied to B0, okay, and then we multiply this by a bracket and one more bracket, 1 plus the taper ratio plus the taper ratio squared, and then this will be divided to the taper ratio multiplied by 1 minus the taper ratio. So you can see how many times we use the taper ratio, and it's quite important for estimating the chords. And sorry, I did a mistake here. Here is 1 plus, right? Yeah. And this makes our median aerodynamic chord to be located at, to be long 2.03 meters. So it is going to be more to the inner part of the wing, which is actually not a surprise. So once we have this, we can now choose the front wing sweep. And normally, the aircraft that are traveling with transonic speeds are having wing sweep of about 10 degrees, and actually this is the degree that I'm going to be using. And you should know that it is very important, the more speed aircraft produces, the more sweep it needs, okay? Because that really helps for the aerodynamic characteristics on high speed, okay? Because at high speed we have higher shock waves, and the negative effect of the shock waves on the aircraft is basically reduced with increasing the sweep angle, because this reduces the effective Mach number on the wing. But about this also you can check in the aerodynamics course. I would advise you you take a look, because it's quite useful for understanding this concept. Now, since we choose a sweep angle of 10 degrees, now we can determine the rear sweep and the crank sweep. Okay, and the crank is usually let's say, so this aircraft here, it doesn't have a crank, our will have, but I will show you here on the picture actually. So some aircrafts are having a crank, and the crank is used for actively changing the flow distribution on our wing. So let's say if we would have a crank, our wing is not going to look like this, but it will look at like something like this. So straight line until here, and then there is an angle here, right? And actually on A320 and A330, they all have this type of crank in order to control the flow distribution on the wing. So the crank is actually this one. Okay, so this is the crank. Set this. Now we can estimate first the rear sweep with this equation here. Okay, and this will give us the Arcus tangents of the angle we need. So then we will need to estimate the actual angle. So here this will be equal to A tan, and this is Arcus tangents in Excel, and then bracket 2 divided by L multiplied by bracket BR minus B0 plus L divided by 2. So now we have L divided by 2, and then we multiply all this, and actually I will put it in brackets so we ensure that this is a closed calculation. So this is multiplied by tangents, okay, and the tangents will be of the previous angle, which is equal to 10. So will be tangents of this angle, and that's it. We close this bracket, and I will close the other one. And there's one more, right? Yeah, to close Arcus tangents. And now we can see that the Arcus tangents for our angle is 0.39, and later I will estimate this angle in degrees, but let's first estimate the crank sweep as well. So the crank sweep will be again equal to Arcus tangents. So Arcus tangents, and in the brackets we will again say 2 divided by L multiplied by, so BK. Actually, I made a mistake here. This is a BR, and you will see this in your workbook as a BR. So this is a BR minus B0, okay, and this will be divided by 4 plus bracket L divided by 2, L divided by 2 multiplied by again tangents of this angle. So I write tan, so tangents of 10, and we're ready with this equation, and we get 0.93 for the Arcus tangents of that angle. And now let's see what are these angles in degrees actually, and then we're going to choose the dihedral angle. Okay, so on web you can quite simply find the Arcus tangents calculator, and I will basically copy this and paste it here, and then when we calculate it, this is equal to about 21 degrees. Okay, so here I will write 21, and then the crank sweep, it's going to be, let's see, it's going to be 0.28. Okay, so now we found all the sweeps on our wing, right? And that's it. And for the dihedral angle, I will choose about 5 degrees. This is a common value for this angle. And if you don't know what this angle is, it is very simple. So if I place an arrow of 90 degrees to the aircraft, okay, and if I select one more that is a perpendicular here, okay, I will actually make it in red. So you see this line here, and now I will also make another line which refers to the wing. Okay, so the wing, as you can see, is not exactly straight, and basically the dihedral angle is exactly this one here between these two lines. Okay, so this here is the dihedral angle. Let's make it blue. There we go. So this here is the dihedral angle, and as you can see even from the drawing, you can say that this angle is not quite high. So this is about 5 degrees. Okay. So what I will do, I will actually copy and paste this table here, and I will actually paste it only by values. Okay, no, actually I will not do that. Better just to copy and paste it inside our workbook. So I will copy this and also the engines. Here we go, as we estimated our wing now, and I will simply place it here. Okay, let's place it now in the middle. And I have some typos here. I will try to correct them before uploading this. Okay, and the only difference here, I will just change the values of the crank and the sweep angle to the values in degrees. So it's 28, and this one will be 21. And I will just write here that all the values are in degrees here, right? Here we go, and the rest of the values here, I think are in, so S is in meters, then these ones are in meters, and this is meter squared, and this in DA newtons. Okay, so now you have, guys, your table here finally. And here are all the parameters that the manufacturers are going to be using in order to build the aircraft that you designed. So actually that was the most complex part of this section here. But before ending up for today, I will first also copy this table and I will place it here. So I will remove this one, and I will simply place our table so we're aware on what we're using for our aircraft and how is it going to look like. So that's pretty much everything for this lecture, guys. I hope you enjoyed and you really understood how to estimate your wing. And in the next sections, we're going to emphasize on the horizontal, vertical, and the control surfaces, which are honestly, in my opinion, way more simple than what you've already done. So that's it. Thank you very much for watching, and I will expect to see you in the next videos. Hi everyone, in this video we're going to solve the geometry of our horizontal surface. But before going to the workbook, I just want to state what is the horizontal surface and what are basically the different surfaces on the aircraft as a recap before we start our actual job. So as you can see here, there is a picture of a plane and the horizontal surfaces are marked. So you just need to mention, and you just need to know actually, that the horizontal surface has nothing to do with the elevator of the aircraft. The elevator is a part of the whole surface. So in that section here, we're going to first estimate what are going to be the characteristics of our horizontal stabilizer or of our horizontal surface, which is basically the same. And the elevator will be estimated later, so its geometrical characteristics are obviously going to be different from the ones of the whole horizontal stabilizer. And actually the same is for the vertical stabilizer or the vertical surface, but about this we will talk a bit later in another videos. So here we are in our workbook, and you can see that the section for the horizontal surface geometry is actually not that big. And here we're going to use one very interesting technique. So as you can see, there is one equation for the static moment, okay, and we want to keep the static moment of the horizontal stabilizer to be between 0.8 and 1. So what I'm going to do here is that we are having this table, as you can see, okay, and the first thing I will do, even I don't have all the rest of the variables, I will write the equation for the static moment, and some of the parameters for the horizontal stabilizer we're going to add in this table, and then see if our static moment is in the range between 0.8 and 1.1. If it is not, then we're going to choose another characteristics in order to meet the static moment so our aircraft flies properly. So let's actually write the equation. So this will be equal to the surface of the horizontal stabilizer. So I write a bracket, the surface, which is recorded here, So this multiplied by the LSH. So the LSH is this one here, but it could be found by simply dividing or simply multiplying actually this equation here, SHS divided by BAHS, okay, and this should be also multiplied by BSASH, okay, which is this one. And in that way we're going to get LHS, if it makes sense, right? So the whole this sentence should be divided by bracket S of the wing, so we have S of the wing here, multiplied by the BA, which is the median chord of our wing. So this is multiplied like this here, and now we have our equation. And for now it's equal to 0 because some of the values here we don't have them yet. So let's choose some of our variables according what is proposed by the other aircrafts and by the studies completed for them. So the BHS divided by LHS, which is the distance from the center of gravity to the aerodynamic center of the horizontal surface, divided by the median chord of our wing, should be between 2 and 3, so I will take it as 2.2. And so you can imagine the distance from the center of gravity. You actually saw it on this picture. So actually this is the distance. So here is the center of gravity of the aircraft, and the distance L is between the horizontal surface, okay, and the center of gravity. That's it. So we're gonna take this distance divided by BASHS to be equal to 2.2. We will choose aspect ratio to be equal to 4, and also the taper ratio will be equal to 3 in this case. And then we need to choose our sweep angle, and I'm actually going to choose a standard 35 degrees of a sweep angle. Then the dihedral angle, I will choose it to be 0 because normally on the horizontal stabilizers there is no dihedral angle, so it is usually straight to the horizontal plane. And that's it here. Then for the area I will choose 13, okay, but this will probably change. I'm just guessing here, but I think it should be about 13 square meters. But let's see, maybe we'll change this number after we see how this equation stands. So now we can estimate the span of the horizontal stabilizer, and this will actually be equal to square root, so it's the same equation as the wing, square root of the area of this surface multiplied by the aspect ratio. So we're going to multiply this by the aspect ratio, and we're going to get that the span is about 7.21, okay, and that's it. So now we need to estimate the inner, the outer, and the median chord. So as we did with the wing, the inner chord will be simply be equal to the taper ratio multiplied by the outer chord. Then the outer chord will be equal to bracket the area of the horizontal stabilizer divided by the span of this stabilizer, okay, and I will close it, and this I will divide it by 2. So here we are getting about 0.9, and finally the median chord, and here we need to state that this is the median aerodynamic chord, will be equal to bracket 2 divided by 3, okay, multiplied by B0HS, okay, multiplied by bracket, and then 1 plus ni plus ni squared, okay. So this is on the upper part of the equation, and I'm basically taking the same equation as the one used for the wing. It is the same logic here, and this will be divided by again ni multiplied by bracket 1 plus ni, and then we close all the brackets, and that should be it. So we're getting about 1.95 for our median aerodynamic chord. And finally we're going to write the equation for the rear sweep. So the rear sweep, as from the equation for the wing will be equal to r costangens, so a tan, and then in the brackets 2 divided by L, and this actually should be in a brackets as well, so this should be in brackets, and this will multiply by BR, so BR is here, so we'll multiply this by BR minus B0, which is this one, okay, plus bracket L divided by 2 multiplied by TG, or tangents actually, so tangents of the front sweep, which we chose to be 35 degrees, okay? So I will select this angle here, and then we can close this bracket, and the bracket for the whole equation, and the bracket for the r costangens. And let's see what we're going to get. So as you can see here, we're getting a negative rear sweep. So we're getting a negative angle here. So in that case, we would need to change some parameters in order to have a positive sweep angle, which is always better. So as we cannot change the inner and the outer chord, we can either change the sweep angle here or some of the other parameters. But let's try to change the sweep angle. For example, if I do like this, so if it is 35.1, or even if I do it 36, then we're getting more and more sweep. But I'll actually do it 35.5. So I get this r costangens here, and now we need to estimate it with our web tool that I mentioned to you in the last video, and I will assess it just in a second. So let's write here the r costangens actually. So I will copy it and paste it, and let's calculate it. So this gives us a rear sweep of 35 degrees, which in my opinion is a bit too much. Let's try to make this one 35.1, and let's see what's gonna happen. So if we make it like this, let's check this r costangens. So now we're getting about 6 degrees here, which is actually quite acceptable. So the sweep angle, the front sweep angle will be 35.1, while the rear sweep will be 6 degrees, okay? And that's fine. And do you remember our static moment that we wrote the equation in the beginning? So yeah, actually this is the formula here, and you can see that it had to be between 0.8 and 1.1, and our value here is 0.91, which means that the parameters that we chose for the scheme of our aircraft will definitely work. So that was it, guys. We estimated it, and now the only thing you need to do is simply to copy and paste the table here. Okay, I will just place it in the middle so it's more representing, and the only thing I will do is that I will change here the value to 6 degrees. So here I will change to 6 degrees, and actually I remove these numbers here because I want to have smaller amount of numbers, especially when we want to present stuff. It is always the best to have about 2 numbers after the point. Okay, and I will also remove this, and then I will save it. So that was it, guys. And here also I have a typo. Yeah, this is, I guess it carried a typo from the previous table, but anyways, now we learned how to estimate these parameters for the horizontal surface, and in the next lecture I will show you how to do the same but for the vertical surface of the aircraft. So we're going to estimate its geometry. Thanks for watching. Hi guys, today we are going to estimate the geometry of our vertical surface, and again you can see that the vertical surface is actually the whole surface of our vertical plane, okay, and this also includes the rudder. So don't worry that in this picture the rudder is showed as a separate thing. The vertical surface includes the whole package, right? And also we're going again to consider the distance of the vertical stabilizer from the center of gravity, which is important for our estimations. And also I must mention that the vertical stabilizer is basically stabilizing the aircraft in the rolling moment. So it stabilizes that the aircraft do not roll freely, okay? And on the other side, the rudder you can control actually the rolling moment in which direction you would like your aircraft to go, but in that topic we're going to dig in the next sections. So today we're going to only estimate the characteristics of our vertical stabilizer or of our vertical surface. So here we are, guys, in the workbook and also in the Excel sheet. Okay, and here I would just need to write, because it looks like I missed VS area. Okay, because this is the area of the vertical stabilizer, and basically here all the equations are absolutely the same. I would say the same as the equations for the horizontal surface. So I will actually, what I will do is I will copy this cell here and I will place it here. Okay, and let's see if we get all the values that we need. So here in the upper part I will write SVS, which is this one, and this will be multiplied by the LVS, which is again this line here, multiplied by the BA, okay, which is this one, BAVS. Okay, that's it, and this should be divided by S multiplied by L, and this is the S of the wing. So here actually I will delete this and I will go up to find the S of the wing and the L of the wing. So this is the wing, and here we go, S multiplied by L, by the wingspan. That's it, and our equation is right here. And of course you're getting 0 because yet we didn't find these values, but now we'll find some of them. So first let's choose the values that we have some idea on what they are. So the A of the vertical surface, just to mention, should be between 0.05 and 0.08. Quite different, quite smaller comparing to the horizontal stabilizer, and this is because the static moment produced by the vertical surface is way smaller comparing to the one of the horizontal one, which is normal. But let's choose the LVS divided by BA. So I will take this to be equal to 2. Then the next thing we will choose is actually the aspect ratio, and the aspect ratio I will choose to be 1, and the type ratio again I will choose to be equal to 3. Then the sweep angle here I will choose 39 degrees, and let's see what's gonna happen. And the dihedral angle, obviously here will be 0 again, because imagine how destabilizing is going to be a dihedral angle on the vertical surface. It's ridiculous. So yeah, there is no point of doing this, that's why it's 0. And the surface area I will choose to be equal to 6.5, and let's see what's gonna happen. Then the inner chord, the outer chord, the median aerodynamic chord, and the rear sweep are basically with the same equations as this one. So in Excel, if I copy the cells here to here, it will just copy the equations and the locations of the new table. And if you have the same locations for the similar parameters between the vertical and the horizontal surface, then these equations will work. So let's try out this. Okay, and for now we're getting an error because here we don't have the value for L, and let's simply write the equation for L, and I'll actually copy it from here. Okay, so you know L is equal to a squared root of the area of the surface multiplied by the aspect ratio. So that should be fine now. And here, as you can see, we didn't need to type all the equations by ourselves because the tables are identical. So for that reason, now you can see that for the span we're getting about 2.5. For the inner chord we're getting 3.8, and this is in meters. For the outer chord 1.27 in meters. Then for the median aerodynamic chord 2.7, and for the rear sweep 1.16, which is actually about 45 degrees. Okay, and that's it, guys. We're ready with the vertical surface. So what I will do, I will just copy it now. I will just copy this table and I will place it in our vertical airfoil geometry area. Okay, so I will just scroll down here and then I will place it right here. Okay, and also you can see actually our static moment coefficient is 0.075, which is exactly in the range that we would like to have it. So I will just place this table in the middle. I will remove the additional numbers that we don't want, and here I will do them by 3 actually. Actually, this angle here is 45 degrees. Okay, and that's it, guys. We're ready with the vertical surface. So now, since we are ready with the vertical surface, in the next section we're going to complete the elevator and the rudder design. That will be quite a short lecture, and then we'll move to the cabin. Thanks for watching. Hi guys, today we're going to do the design of the rudder, the elevator, and actually also the ailerons. So basically today we're going to design all the control surfaces that are on the aircraft, and you will see how simple it is just by knowing the dimensions of the wing, vertical and horizontal stabilizers. And before starting, I just want to mention that these surfaces are called control surfaces because they basically control all the moments on the aircraft, which are the pitch, the roll, and the yaw moment, okay? And each of them is controlling a different moment, so basically they can move the aircraft in any direction in the 3D space. And today we're going to design them quite simply. So here we are in our Excel sheet, and this is basically the section for the elevator and rudder design. And as you can see, they're basically a percentage of the stabilizer or of the wing that they're positioned on. It is quite simple. So for example, for the S elevator, or the area of the elevator, we will have it equal to 0.3 to 0.4. This means 30 to 40% of the area of the horizontal stabilizer. And this is what we're going to do. So I'm going to do 0.35 multiplied by the area of the horizontal stabilizer, which is this one, and then I'm getting 4.55 square meters, which is the area of the elevator. Now the rudder will be equal to about 0.4 multiplied by the area of the whole vertical surface. Okay, so this is 6.5. So here we get 2.6. Then the aileron is about 0.05 to 0.07% of the wing. So I will do it so this will be equal to 0.06 multiplied by the area of the wing, which is this one. Okay, so we're getting here about 1.8 in square meters, and then the aileron span will be equal to about 35% of the span of the wing. Okay, so that's why the ailerons are usually quite thin but long on the wing surface. So this will be equal to 0.35 multiplied by the span of the wing, and the span of the wing is actually here. Okay, then the aileron chord will be equal to about 20 to 25% of the aerodynamic chord of the wing. So this will be equal to 0.23 actually multiplied by, and let's go here up to the wing, and the aerodynamic chord is this one, so by this value here, and here we're getting the chord of about 0.46 in square meters, okay, in meters, sorry. And that's it, guys. We estimated all the values, and here I will again copy this table and simply place it under this section here. Okay, variable. I don't know why I copied this table with so many mistakes, but it is what it is. I will just fix it before uploading it in the website so you can find it in the best way. So let's simply place it in the middle, and also I will again remove the long numbers here. And that's it, guys. We're ready with our elevators and rudder and ailerons actually. So we're done with this section. We're ready with that because we designed the geometry of our wing, the control surfaces and the balancing surfaces, which were the horizontal and the vertical stabilizer. So thanks for watching, and in the next section we're actually going to design our cabin, which is going to be a first class since we're designing a business jet. So you will see the characteristics of the first class cabin and how we're gonna design it. Thanks for watching. Hi everyone, today we're going to start the design of our passenger's cabin by designing the width of the fuselage. And basically the width of the fuselage depends on what you want to have inside the body of the aircraft. And also you need to add some dimensions, assuming the thickness of the walls of the cabin and so on. But basically you can estimate the cabin characteristics with the equation that you can see in front of you. But more about this equation I will talk when we move on to our workbook. So let's do it right now. So here we are in our workbook and actually in the business jet project, and also we're having the worksheet, the Excel worksheet that we're using for our project. And first I would like to talk about this equation that you just saw on the slides. So as I said, the width of the cabin depends on the things that you add inside the cabin. So this equation basically represents, so B2 and B3 are the width of the seats that you're going to have. So usually in the aircraft, you probably notice, I guess you traveled with an airplane, there are blocks of seats, and usually these blocks are of 2 seats or of 3 seats. So simply B2 and B3 represent respectively the width of the 2 seats blocks and of the 3 seats blocks. Then N2 and N3 are representing the number of 2 and 3 seat blocks that we have per a single row, not the total number, but per single row. This equation is actually based for a single row because the width of the fuselage depends on what seats and what equipment you have per single row. Okay, then the C and the N are basically representing the C represents the width of the corridors. So you know, between the seats you need to have corridor in order for the passengers to be able to board and leave the airplane. So C represents the width of that corridor, and N simply represents the number of corridors. It is that simple. So basically when you estimate them, you get the total width of the corridors. And finally B1 and B2 are simply estimating the distance from the seats to the wall and then the thickness of the wall. That's it. And this is how we can find the width of our cabin. So you can actually use this table here that I'm providing for you, and you can see that depending whether the aircraft is first or the second class, you have different dimensions for the seats and so on. So for first class, the 2-seat block for first class have the width of 1260, and this is the value that we're going to use, 1260. Then the number of double seat blocks is 1. So our aircraft, since it is only for 12 passengers, it will have only 1 block of 2 seats per row. Okay, so we're having 1 block here. Then obviously we have 1 corridor with the first class corridor, which is 510. Then there is, as I said, 1 corridor. Then we're going to choose 30 for the inner wall distance, or what is the distance between the seat and the wall. And finally the thickness of the wall will be 120 as described here. Okay, that's it. And now we're ready with this, and we can actually write our equation and estimate it. So this will be equal to, so B2 multiplied by N2 plus, so B3 we don't have, since we don't have the 3 seats, but this will be plus Cn multiplied by the number of corridors plus B1 multiplied by 2, and we multiplied by 2 because we have walls and we have distance from walls on the 2 sides of the cabin, and then this will be summed with 120 multiplied by 2. That's it. And we're getting the total width of our cabin to be 2070 millimeters, which is about 2 meters and 70 millimeters. Okay, so pretty much that's it, guys. This was the width of our cabin, and in the next section we're going to estimate, as you can see, the cabin length, height, and body length. Okay, so thanks for watching, and I will see you in the next lecture. Hello everyone. Welcome back to this section where we're estimating actually our cabin. So today we're going to estimate the cabin length. Since in the last lecture we estimated the width, now it's time to estimate the length of our cabin. and it is estimated by this equation here. So let's go to the workbook where I will describe each component of this equation like we always do. So here is the equation for estimating the cabin length, and each component is described here in the workbook, so you can always check it. So L1 means the distance between the front compartment and the front row. Okay, there is always distance between the front row and the front compartment, and usually for first class this is about 630 millimeters, which is the value we are going to use. Then the minimum distance between the rear compartment and the back row is described by L2, and in our case obviously it will be equal to about 1000 millimeters, as again our aircraft is business jet and we want high quality of our services. Then the number of rows are marked by IR, okay, and then the distance between two seat blocks. As I told you, the seats are placed by blocks, so the distance between two seat blocks is going to be for first class between 980 and 1080. Okay, and you can see how big difference here is between the first and the third class, and this is because for third class, as the tickets are cheaper, the airlines are trying to accommodate as many passengers as possible. That's why this distance is so dramatically smaller for the different types of classes. So let's choose our values and let's write our equation actually. So the front compartment distance, as I said, will be 630. Then the distance from the rear seats is going to be 1000. Then the number of rows actually for us is going to be equal to 6, as we want 12 people on our aircraft. So we have 6 rows of 2 seats. So we have 6 rows, and the distance between each row, in our case, I will make it 990 in order to accommodate everything in our body. Okay, and this is still a first class, if you note. So that's it, guys. Let's now estimate the equation here. And so here we have L1 plus bracket IR, which is the number of rows, minus 1, because imagine if you have 6 seats, you're gonna have 5 distances between them. That's why it is minus 1 here, and then this will be multiplied by the distance between 2 seats, which is this one. Okay, and then we'll simply add the back compartment. Okay, and finally for the cabin length we're getting 6580, and note that this is the length of the cabin where the passengers are positioned. Later we are going to estimate the length of the full body, but about this we are going to talk in the next lecture. So thank you guys for watching, and I will see you in the next video. Hi everyone, welcome to the last lecture from this section when we're estimating our cabin and basically the body of our aircraft. So the first thing we will do is to simply estimate the cabin height, and we're actually going to choose value for the height, and the height will be between 1 meter, 1.9 meters and 2.5 meters. And it pretty much depends, you will see how. And then it is important to mention that the ratio between the cabin length and the height should be about 0.2 to 0.5. So you can see how the seats are positioned here normally, and we want to allow maximum space for our passengers. So let's see how this is done. And once we finish with the cabin height, we're going to estimate the length of the whole body, and we're going to estimate it by this equation here, okay, which dm means basically the diameter of our whole body and so on. Let's move to our workbook where I will explain this in more detail. Now for the cabin height, I'm going to choose actually a value of 2100, so we'll allow enough space. And then for the body length, we will first need to determine these coefficients: the front, the rear extension, and the medium section diameter. Okay, so usually the front and the rear extensions are between 1.2 to 2 and 2 to 3 respectively. okay, and the diameter can be basically estimated from this equation here, where the S mu is the section area, as you can see. So the coefficients, I'm gonna choose them. So the first one will be equal to 1.5. Let's take some average values and see what happens. And then the other one will be 2.5. And as I said, this is usually estimated by this equation here, but since we already found our fuselage width that you can see here, basically the diameter of the whole cabin is the same as the width of our cabin. It makes sense, right? And this is just because our cabin is a circular. So it doesn't matter if you are taking the width or the height of the cabin, they should be always the same. And for that reason, I'm going to choose them equal to 2100, because the width that we estimate was about 2070 millimeters, and it makes sense that the cabin height and the cabin width are a little bit higher than the width that we estimated, okay? Even they usually should be absolutely the same, but we're just taking some measures in order for our project to have additional safety precautions. So finally we can estimate the body length, and the body length, guys, will be equal to this equation here. So basically, so this will be equal to LC, which is the cabin length, okay, plus the front extension of the aircraft, okay, multiplied by the diameter of the aircraft, which is this one, plus the back extension of the aircraft, which is multiplied by the diameter. It makes sense, right? And this is how we're getting the value for the whole body, which is going to be about 15,000 millimeters or 15 meters, okay? It's 14.98. So that's it, guys. You estimated the whole cabin length, and here I will just fix a typo variable, okay? And now you can place your table under the section where you estimate the shape of your cabin and of the body of the aircraft. So I will simply place it here in the middle. Okay, that's it, and we're completely ready. So that was it, guys. This was the section for building your body by estimating the fuselage width, cabin length, cabin height, and body length. Okay, this is everything. Now you know all the dimensions of your aircraft, and the next thing that we're going to do is simply to estimate the masses of the aircraft and how they are going to be positioned. So thanks for watching, and I will see you in the next section. Hi everyone, welcome back to the course, and in this section we're going to re-estimate all the masses of the aircraft using the data that we already have. So we'll start by today estimating the mass of the wing with this beautiful equation here. It is quite long, but we'll have to solve it, okay? So let me just go over the coefficients that we're going to be using here, and you can understand on what the wing mass is pretty much dependent. So first of all, we have the coefficient related to the mass construction. So we care about how the wing has been constructed, and this coefficient is normally equal to 0.9 for the honeycomb structures or 0.95 for rived and glued wing. And actually, for me, in my opinion, this one is the best, the rived and the glue wing. So this is the coefficient we're going to use for the construction, and I'm going to write here 0.95. Then we need to choose the mechanization coefficient that you can see in the project. I uploaded it here. So this coefficient in our case is going to be 1.15 because our aircraft will have full mechanization. So this coefficient will be 1.15, and then we have the material coefficient, which determines from what material the wing has been built. And actually here you can see the most common materials for building a wings these days. So I would say that in our case the material for the wing will be D16, which is quite common material, and for that reason this coefficient will be equal to 1. And then we have the unloading coefficient phi, which is normally about 0.7. I will write it 0.68. Then you have the overloading coefficient that we will need to record, and as you can see, the overloading coefficient is between 5.5 and 6, and as our aircraft do not maneuver too much because it's a transport aircraft, for that reason I'm gonna write this coefficient as 5.5. Then we have the wing aspect ratio, of which we already have a value, and the value is 8.5, so this is the aspect ratio of our wing. Then we have the wing area, for which we also have a value, and it is 29.918, and you can get this information from our estimations for the wing area. Then you have the wing structure coefficient. So the wing structure coefficient is pretty much determining the strength of the wing, and normally I actually didn't write it here, but it's normally equal to 0.9. so here I write 0.9, okay, for the materials that we're using, so 0.9 here. And then we have the core wing thickness, okay, and basically this is the thickness of the material that we're going to use for the wing, and normally the thickness is equal to about 0.1. I will make it 0.12, and this is the thickness in the core, okay. And also the thickness through the wing area could be different, but what we care about here is how thick the wing is on the core. Then we have the crank sweep angle, which we already have, of course, and this was equal to 0.488692. You can see it from the previous tables as well. I will actually just find it for you, that you can see that we actually estimated it. So it is actually this one up there, and the value is actually different, so it's good that I actually had a look at it. So it is this one, the crank sweep, okay, and then we will need to have here the taper ratio, which we already estimated, is equal to 3. And finally, the core to tip thickness ratio, and I will make actually this equal to 0.12. Actually, I'm gonna copy this value, divided by 0.11. Okay, so this is the thickness to the core, and then 0.11 is going to be our thickness to the tip. Why I didn't include it in a different coefficient is just because we will need to use this particular value only in this case. So once we have all the values here, now we can write the equation, and believe me, this equation is quite long to write in Excel, so let's get started. And so this one will be equal to 1.15 multiplied by 10 to the minus 4. Here we go. So this I will multiply by the K mech multiplied by the K of the construction, and this will be multiplied by the K of the material, okay, and then I will also multiply this by the unloading coefficient, okay. So until here we are ready. So this is multiplied by a bracket, and here in this bracket you need to be very careful. So I'll create one more bracket here, and I will select the NE, which is the overloading, multiplied by square root, okay, and this is square root of S, right? That's it. Let's close the other bracket as well, and then I will divide this to the SQRT, so square root, and yeah, so this is all square root. So here inside the square root I will place the wing structure coefficient, okay, and this will be multiplied by the core wing thickness, and then multiplied, and here this one is a bit tricky because you need to have cosine of the X of the crank sweep, but actually here this angle is in arctangents, okay, it's estimated in arctangents, and what we need actually is the value of actual angle in radians, okay. So I will select it for now, but then we will need to change this value what we recorded here, because if you don't know, Excel takes the angles only in radians but not in degrees, not in arctangents as well. So for now I write cosine, okay, so cosine of that angle, I will close it, and actually the whole cosine will be in bracket, and I will make it to the 1.5, okay. And once you do this, then close the square root, okay, so we're out of the square root, and now we're out of this division here. Then let's multiply this by another two brackets, okay, and then select new plus 4, divided by new plus 1 and close the bracket, and we'll multiply this by bracket 1 minus, and then so we have bracket mu minus 1 close the bracket divided by bracket ni plus 3. Okay, so now when I attempt to close this, it doesn't do it because some brackets needs to be added, and Excel will add them by itself. Okay, so you can see the whole equation here, but as I told you, we did a mistake here because this angle here should be in radians. So what I will do now, I will simply write in Google degrees to radians, and our angle in degrees was equal to 28. So I'll write here 28 degrees, and we're getting 0.88. Actually, this was the reason why in the beginning I included this value, because I estimated it obviously before starting this lesson here. So here we use the value 0.488, and that's it. So we're ready here, and you can see that the relative mass of the wing is 0.014, which is actually something that is not expected, and I would say that we have some mistake in the equation because this mass is way too small for our wing. So as you can see, we actually didn't use aspect ratio and actually didn't include it here in the equation. So actually I will change right now the equation here, because we also need to add the aspect ratio where is any on the same place. So I will simply write a symbol and then lambda here. Okay, so once I do this, I will also add it in here as well. So here I will add lambda and multiplication, okay, here on the upper part. And another thing that I actually need to change is that some symbols were actually outside the square root. So this cosine of the crank sweep should be outside our square root. So I will also fix this by here in the square root. I will simply add one bracket. Okay, so now we have square root of this, and then I want another bracket just to close this part of the equation. So now we have a square root of these two multiplied by cosine of this angle to the 1.5, and that's it, guys. So here you can see this is our final value. It's 0.1389, and this is the relative mass of the wing, the true relative mass of the wing from the whole mass of the aircraft. Okay, so we're ready with that actually, and since we know the mass of the wing already, we can continue in the next lectures with the masses of the fuselage, the control surfaces, the landing gear, and so on. So that's it gonna be for today. Thank you very much for watching, and I will see you in the next. Hi guys, as we estimated last time the mass of the wing, today I'm going to estimate the rest of the masses of the construction of the aircraft. So we have a construction which includes the wing, the fuselage, the control surfaces, and the landing gear, and we have other parts such as the power plant, the passengers, and so on. So what is going to be our aim today is to find the final value for the construction mass, which include the four masses that I just mentioned to you. So we'll start by estimating the final relative fuselage mass with this equation here. And you shouldn't get actually very scared from this type of equations, because you simply can type them in Excel, and it's very simple, as you saw from the last lecture how we did a very complex equation just with one step in Excel. So the first thing that I'm gonna do, let's talk about the coefficients. First of all, you have the KEP coefficient, which denotes whether the engines are mounted inside the fuselage or not. Simply, if the engines are mounted inside the fuselage, then it is equal to 1.14, and if they are not, it is equal simply to 1. So in our case, our engines are not mounted in the wing, but they are mounted inside the body, and for that reason this coefficient here will be equal to 1.4, and I will type it down. Then the cabin pressure coefficient is something that we can actually talk about it a little bit. So the cabin pressure coefficient is the pressure that you need to apply to the cabin in order the passengers to survive the high altitude. So what the companies are normally doing, they're adding a pressure in the cabin when the aircraft is at altitude more than 3,000 feet. Okay, so once the aircraft is 3,000 meters. So once the aircraft is over 3000 meters, then the passengers cannot breathe normally if we don't apply pressure in the cabin. So we simply apply pressure in the cabin and not oxygen as well, in order the pressure there to be enough for life, or for the passengers not to feel uncomfortable. So that said, applying pressure inside the cabin also causes a structural difficulties for the whole cabin. This is the same if you blow into a balloon. The balloon expands and expands and then it blows, right? So what the cabin is doing, it tries to blow, right? And the only thing that saves the cabin from blowing is pretty much the structure of the cabin. And for that reason we have these coefficients like the pressure coefficients, or the pressure, we care about the pressure inside the cabin, so we know what materials and how heavy they are going to be used for the cabin. So that said, let's continue with typing the pressure coefficient in the cabin. So the pressure coefficient in the cabin is going to be 0.8 for us to maintain a standard conditions for the passengers to survive the flight. Then the AOM is the length of the body in meters in this case, so you know that you estimated the body to be equal to 15 meters. Actually, I can show you this from here. So 14,980, which is equal to 15 meters basically. And then we will need the initial aircraft mass. So remember, when we were estimating the mass for first time, we estimated to be equal to 13,500 kilograms, right? And I also mentioned you in that case that there is some discrepancy in our estimations, and I assume that the mass is going to be about 15,000 kilograms. So I just want to mention that here we're going to use this 13,500 kilograms, and this is basically how the project is going to be developed from one masses to others. So here we're going to re-estimate the masses based on this mass, which is 13,500 kilograms, and once we find the relative coefficients for each mass, you will see that the actual mass in the end, once we re-estimate it, is going to increase and is actually going to be close to this 15,000 kilograms that I mentioned in the first video. But for now, for M0, we use the first mass that we assumed, which is 13,500 kilograms. So here I write 13,500 and we are ready. Now I can use this equation that I mentioned in the notebook. So this will be equal to 1.14 multiplied by KEP, which is this one, multiplied by 1 minus 0.4 multiplied by the pressure in the cabin. Okay, then let's close the bracket, and this will be multiplied by LM to the power of 1.5, and this will be multiplied by M0 to the power of bracket minus 0.75. Okay, so that's it. Let's press OK. And I just missed the one here, so I'll add it in the K. Okay, and now we're finally getting 0.04 for the mass of the fuselage, which is actually a normal thing. So it's about 4%. So the mass of the fuselage is about 4% of the mass of the whole aircraft, and this is normal because imagine the fuselage is simply as like a tube. So the only thing that weighs is the walls of that fuselage. Okay, so that's why it's about 4 to 5% is normal for the fuselage of the aircraft. Then let's estimate the control surfaces. Okay, and we have the equation here. So first of all, we have the velocity coefficient, which is this one. Then we have the maneuverability coefficient, which is Km, and actually I'm gonna type it down. So Km, for our case, we would like our aircraft to have a good maneuverability, so I will place 1.5 here just in case. Then we have our cruise speed, which I'm not going to write because we already have it and we're going to use it from the previous sections. And then we have M0 and the surface of the tail. Okay, so this is simply going to be, so actually I will write this down. So S tail will be equal to the vertical surface area, okay, plus the horizontal surface area, which is this one, right? So let's type this, and now we get that the area is 19.5, and I think this is meter square, so I'll just write this, okay. And then let's estimate kV. So this will be equal to 0.43 plus 1.02 multiplied by 10 to the minus third multiplied by the cruise speed, which we have it here in 780. Okay, that's it. Let's close this bracket here. Oh, sorry, we even don't have a bracket. So that's it, guys. So this is equal to 1.43, which is a good number for this type of the coefficient, for the velocity coefficient. And now, since we are ready, let's estimate the final relative mass of our control surfaces. So this will be equal, and actually here I missed the sign equal. So this will be equal to bracket kV multiplied by km, close the bracket, divided by m0, which is this one, okay. And actually I'll place all this in brackets. So the whole thing in brackets will be multiplied by 4.4 plus 0.8 multiplied by 10 to the minus third, and this will be multiplied by m0 as well, okay. So m0 here, okay, and the whole equation here is going to be multiplied by the tail, okay. So I will actually type it manually because it already covered it. So this will be F213, okay, that's it, okay. And let's actually reduce the size of the surfaces by reducing the maneuverability coefficient, because as I mentioned you earlier, even though we would like our aircraft to have more maneuverability, we might not need them. So instead I'm simply going to use the low maneuverability coefficient. In order, you can see how we can decrease now the mass of the surfaces of the aircraft significantly, and this is because the low maneuverability aircrafts simply need less mass of their control surfaces. That makes sense, right? So that was it, guys. Let's continue with the landing gear relative mass. So the first thing we are going to write is the landing gear material coefficient, which in our case is going to be 0.7. Then we have the aerodynamic coefficient of the landing gear. So this means that if the landing gear have the shape, an aerodynamic shape, then this coefficient is 1.2. If they don't have this type of shape, then it is 1. So in our case it will be 1.2, because we'll make we would insist our landing gear to be with aerodynamic shape for less resistance in the flow. And then we will do the landing gear height, which you can check in internet, but the standard height of the landing gear, it's actually about 1.5 meters for our type of aircraft. Then the tire clutch, or whether we're gonna have chambered tires or unchambered, is going to be noted in this coefficient here. So usually for chambered tires we have this coefficient equal to 1 K tires, or for unchambered we are going to have it equal to 0.93, which is actually not a big difference, and for that reason I will simply write it to be 1. And finally, the pressure in the tires for the aircraft is usually 12 atmospheres. So if you compare this to the one of your car, which is probably about 26, you can see how the tires are having way less pressure in them, and this is actually normal. The bigger the space inside is, the less atmosphere you need inside your tires. So let's write now the equation for the landing gear relative mass, and this will be equal to kmt multiplied by the kfl multiplied by bracket multiplied by LH, and there I wrote it HL, it doesn't matter. So I will simply multiply this plus 11.3, and this will be multiplied to 10 to the minus third, and then plus 0.625 multiplied by KTR, okay, multiplied by bracket, and here we will do a square root of the PTR. So write SQRT and then PTR, okay, and we will divide the SQRT by D bracket 1 plus F219, where is the PTR. Okay, so let's close the first bracket and the second one, and then I'm simply going to add 0.005. Okay, that's it, guys. And here the mass is a bit too high, as you can see, and this is because here it's actually 0.0625. And you know, I also do mistakes, we all learn. So yeah, actually I will also change it here in the equation. So here is going to be 0.0625, and you can see that the mass of the landing gear is actually 0.038. Okay, and note something interesting, that I don't know if you would expect that, but the mass of the landing gear, it's quite close to the mass of the fuselage of the aircraft and to the mass of the control surfaces of the aircraft. And this is something normal because it's a really big piece of the aircraft. That's why you need a separate estimations for it. So the landing gear is actually not a small bit from the aircraft mass, and its mass is completely equal, and it's even higher than the one of the control surfaces, and it's quite close to the mass of the fuselage. So now finally, to simply estimate the construction mass, we simply need to, actually I'll write it here with sum. Okay, so you can simply do a sum of this. So here I'm pressing control, okay, and simply selecting every variable, or you can simply add them, okay, just with the plus sign, it doesn't matter. Okay, so you can see now that the construction relative mass is 0.25 of the mass of the whole aircraft. So the mass of the wing, fuselage, control surfaces, and the landing gear is 1/4 of the total mass of the aircraft, right? So that's it, guys, for now, and in the next lecture I'm going to show you what percentage usually the mass of the power plant is from the total mass of the aircraft. Also, we're going to look at the equipment that is on board, we're going to estimate it, and also we're going to talk about the real fuel mass, which I need to change this. So that was it, guys, for today. Thank you very much for watching, and I will really expect to see you in the next lecture. Thanks for watching. Hi guys, today we are going to talk about the power plant, the equipment, and the fuel mass, as I discussed in the last lecture in the end. So let's do not lose time and simply get started. So here in this section we're going to estimate this, and the first thing that I'll write is actually the power plant mass, and you can see that usually the engines are between 0.05 and 0.1 of the total mass of the aircraft. So this means that they're between 5 and 10% of the total aircraft mass, and in that case I will do it 0.77 just to have some average number. So this means that the power plant 0.077, sorry. So this means that when you multiply the whole mass of the aircraft to the 0.077, you should get the total mass of the power plant. So next, let's estimate the equipment mass of the aircraft. And to estimate it, we actually need the aircraft loading relative mass. Also, we need the range and also the cruise velocity of the aircraft. So the cruise velocity, we know it at 780 kilometers per hour. The range, as you remember from the project, is 300 kilometers, and then the relative loading mass is going to be equal to the loading mass, the actual loading mass, divided by the M0, or the initial estimated aircraft mass. So here this will be equal to the aircraft equipment which we actually estimated, and it's here. So this is basically the crew plus the loading mass, okay? So all this divided by the takeoff mass of the aircraft, okay? And as you can see, this is going to be equal to 0.117778, and actually I made a mistake here because this is not the equipment mass but the loading mass, so I will just copy and paste it here. So actually I'm cutting it and pasting it so I can keep the equation, right? Let me just fix that cell here to be representative. Okay, so we're good now. And now, since we have all the parameters here, I can finally estimate the aircraft equipment relative mass. So this will be equal to 200 divided by m0, which is our initial aircraft mass, plus 0.02 multiplied by the loading mass, okay, and this will be multiplied by a bracket 1 plus 0.1 multiplied by a bracket, and then the range divided by the cruise velocity. That's it. And then plus 0.08. Let's see what I missed here. So yeah, I can see that I missed a bracket. So here I need to close this bracket, okay? And then this will be equal to 0.098. So it's almost so it's actually almost 10% of the total mass of the aircraft, which is quite a lot. I mean, the whole equipment and the loading of the aircraft, it's actually quite a lot. So finally, let's estimate the fuel mass, and obviously the fuel mass is quite a significant part of the total mass of the aircraft, and here this will be equal to the mass of the fuel, which we have it here, the fuel mass, okay, divided by the takeoff mass, right? So this is giving us 0.31, and you can see that the fuel, just the fuel, is 30% of the mass of the aircraft. So the fuel alone is more than the mass of the whole construction of the aircraft, okay? And this is, as I said, quite significant part. So that's it, guys. We estimated basically everything that you needed to know for the mass of the aircraft, and this is actually the end of this section. But in the next one, it's gonna be actually really interesting for you. It will be the final section, and there we're going to do the balancing characteristics of our aircraft. Hi everyone, welcome to the final and the most exciting section of this course. And in this section we're actually going to balance our aircraft by estimating its static horizontal moments. And why this is important? So first, it is very important that we know the relative position of the wing, the body, the power plant, and the surfaces of the aircraft. So we know how it looks like, right? And I bet that you can imagine how an aircraft looks like, but we are engineers. We want to design it specifically. So for that reason, we need a specific distances for our elements. And why we need these distances? Because we want to estimate the balance of the aircraft. We want the center of masses to do not be too forward or too rearward on our aircraft. And this is what we're going to be doing in this section. We're going to estimate all the moments produced by the different components of the aircraft by determining their position and then estimating these moments using also the weight that we used in the previous section. And after we estimate these moments, finally we're going to be able to actually estimate the balancing characteristics, which are represented by the parameter xm star. Okay, so how you can find this xm star? So first you need to have xa, which is the coordinate or the tip or of the median aerodynamic chord. Ba is the length of the median aerodynamic chord, and xm is the center of the masses. So as you can see in the previous equation here, we're looking for the sum of all the moments produced by the different components of the aircraft. So once we summarize these moments, we're going to find the exact position of the center of gravity of our aircraft, and then we use this position in order to find our balancing characteristics. And it's actually very important here, and let's actually go to the next slide. It's very important to know where is the origin of your coordinate system. So in our case, the origin is going to be on the nose. So the 0 is going to be on the nose, and then we're gonna estimate the position of the different components based on their distance from the nose of the aircraft. And actually it doesn't matter from where you take the origin, but it is important that it is always in the same place, obviously. So here you can see the chapter for the balance characteristics. And before starting, I just want to mention that we're going to estimate the balancing characteristics for the four major cases that aircraft is going to be experiencing in the real world. So the first case is going to be the maximum takeoff mass. Then we're gonna have the fully equipped aircraft without fuel. Then the full fuel tank without any load, and finally an empty aircraft. And we're going to estimate each case because we want the balancing characteristics to be applied to each case and to be sure that our aircraft is balanced in all these scenarios. So as a matter of fact, actually the final balancing coefficient should be between 0.2 and 0.3, and this will mean that your aircraft have a good balance. Okay, so this is what we're looking for, and this is what we're trying to achieve in this section. So that was it from this overview section, guys, and bear with me to the next one, where I will estimate the real mass, the true mass of each component of the aircraft, which is actually now going to be quite simple since we know the relative mass. So thanks for watching, and I will see you in the next lecture. Hi guys, today we are going to estimate the real mass of each component in our aircraft, and for that reason I use this table here, right? So before actually doing this, I want to place the table that we used and we did complete in the last lecture. I simply want to place it in our project, so we're certain and we follow our scenario. So first of all, I will do one thing that is called cell format, because I want all the cells to have the maximum number of values of, let's say, 3 after the comma, right? Okay, so I will press OK here, and you can see how these values here have changed. And now, since we are ready, I will just copy and paste this table in our project, so you have it there, and I will place it just in the final of this section. Okay, and let me just fix the typos here, and we can actually continue with the next section. So now we're ready here, and let's start estimating the masses of the aircraft. So first of all, we have the relative mass of the wing, and this will be equal to the mass over here. Okay, the relative wing mass. Then the fuselage mass, we have it here. Then the landing gear mass, or the relative landing gear mass, we have it here. Then the whole construction mass is here. The power plant mass is here. The equipment mass is here, and actually here it's equipment, that's it. Then the aircraft loading mass is here. The fuel mass is here, and finally the control surfaces mass is over here. Okay, so these are all the relative masses we have, right? Now I will show you how you can estimate all the masses just with one step. So first of all, I will select the relative mass here, and obviously we need to multiply it by the total mass of the aircraft, which is this one, 13,500. So I will simply multiply them, and here I will just press a dollar sign. Okay, and what this means is that when I drag this cell down, the dollar sign will prevent this value from changing. So it will always multiply the cell that is in the F column, okay, but we'll keep the value of the mass. So I will press OK here, and here I will drag it, and these are actually all the masses of the aircraft. And if we just have a look at this one, so it uses the relative mass here, but it uses also the initial aircraft mass here. So that's it, guys. We estimated all the masses, and actually now if you see, I'm gonna sum all the real masses that we estimated now, and let's see how much is the total mass of the aircraft having all these masses here. So I will simply select totals, and then I will select sum. So now you can see when we sum all these fields here, okay, when we sum all these fields here, we're getting, actually, I'm quite surprised, but we're getting just 45 kilograms less than this 15,000 kilograms that I mentioned earlier our aircraft will finally weigh. So that was it, guys, for today. I will actually copy and paste this table inside our project, and I'll actually paste it right here just before our aircraft balancing table, so a person that looks at your project can simply see the mass of the aircrafts before starting to do the balancing. Okay, so that was it for today, guys. It was actually unbelievably quite fast lecture today because we estimated the mass quite fast with Excel. So that was it for today, and in the next lecture I will start estimating the aircraft balancing characteristics. Thanks for watching. Hello everyone, today we are going to start our balancing estimation by starting estimating the balance of the construction of the aircraft. So you can see here I already chose what is going to be the distance of our components from the origin of the aircraft, and actually I will display here the picture so you can actually see what I mean. So here is an example of the position of some of the masses of the aircraft. Obviously, the wing and the fuselage, we aim them to be in the center or in the middle of our fuselage. And as the aircraft is long 15 meters, now we can start positioning our components. So first, what I will do is to position the wing and the fuselage exactly in the middle of this 15 meters, which is at 7.5 meters, and they are positioned in the middle of the body. Then the fuel is usually a little bit rear comparing to the wing position, because as you can see, because of the sweep wing angle, actually the mass of the fuel is concentrated a little bit backwards comparing to the wing position. Obviously the fuel is going to be located in our wings. Then the power plant is at 7.5, and it usually, this picture is a bit tricky, but at 7.9, and actually they are going to be a little bit forward, just close to the wings. Okay, there's gonna be the power plant, and actually this is a mistake here, it's actually 9.75. okay, so I mean it's not that close to the wings, but it's just a little bit forward comparing to the horizontal and the vertical surfaces. Then as you can see, the horizontal and the vertical surfaces are almost in the end of our body, so their mass is located in the end. And if you think about it, there are some components that are rotating the aircraft forward and some components that are rotating the aircraft backward compared to the center of gravity. And this is what we're trying to do, to estimate where exactly is going to be the center of masses and maybe to reposition our components. So this is it. This is how we chose pretty much the basic components of the aircraft. I'm just going to talk about, for example, the cabin crew. Obviously, it is going to be located somewhere on the front. For example, the pilots. The mass of the passengers is always taken in the middle of the aircraft, okay? And the same accounts for the load. We also take them there here, because usually how we position the passengers depends on how many passengers there are. If there are two, normally we position one in the front and one in the back for the balancing characteristics, if we think that this will make any difference to our total aircraft balancing. And pretty much that's it, guys. This is how we can position the masses. And now let's start estimating our forces and moments. So first we need to estimate the force produced by each component, and the force is simply the mass multiplied by the distance of the origin of our coordinate system. Sorry, obviously this is actually the moment, and the force is simply the mass multiplied by the Earth's acceleration. So here I'll actually estimate first the forces. And as we don't want our forces estimated in Newton, but in dA in Newton, everything will need to be estimated by 0.1. Okay, so I'll simply write here equal to 0.1 multiplied. Actually, you know what I'm gonna do, which is actually going to be quite fast. So here in this cell I'll actually write equal to 9.81, which is the Earth acceleration, multiplied by 0.1. okay, and then each cell here we're going to estimate with this one, and I will show how this is done. So here I will simply write equal to the wing mass, the total wing mass, which is this one, multiplied by this mass here. Then the next one will be equal to the fuselage multiplied by this one again. Next, the horizontal surface. So let me find it. So we have the control surfaces. The horizontal surface will be equal to the total control surfaces multiplied by this coefficient here, multiplied by 0.4, because usually the horizontal surface is getting 4% 40% of the weight of the tail, while the vertical surface is more heavy and it takes 60%. So that's it here. Then the vertical surface is going to be equal to, again, the control surface multiplied by the vertical direction multiplied by 0.1 multiplied by 0.6. Okay, and this is basically the force produced by the vertical surface. Then the front landing gear will be equal to, obviously, this coefficient multiplied by the landing gear multiplied by 0.3, because it gets a 30% from the total mass of the landing gears. And finally, the main landing gear will take 70% of the mass of the landing gear, so multiplied by 0.7. And pretty much that's it for the construction of the aircraft. So we're done here, guys. Then we need to estimate the moment, and you can see that the moment is equal to m multiplied by g multiplied, so this is simply the force multiplied by the distance, and this is how we get the moment. So let's write that this one is equal to 7.5 multiplied by the force, and I will drag this down to get the rest of our components. So these are basically all the moments produced by the construction of the aircraft. So that was it for today, guys. I don't want to make this video too long, so I will simply continue in the next one when estimating the power plant, equipment, cabin, fuel, load, and the passengers, the mass of the passengers, and the moments produced by them. So thanks for watching for now, and I will see you in the next video. Hello everyone, today we are going to start our balancing estimation by starting estimating the balance of the construction of the aircraft. So you can see here I already chose what is going to be the distance of our components from the origin of the aircraft, and actually I will display here the picture so you can actually see what I mean. So here is an example of the position of some of the masses of the aircraft. Obviously the wing and the fuselage, we aim them to be in the center or in the middle of our fuselage, and as the aircraft is long 15 meters, now we can start positioning our components. So first what I will do is to position the wing and the fuselage exactly in the middle of this 15 meters, which is at 7.5 meters, and they are positioned in the middle of the body. Then the fuel is usually a little bit rear comparing to the wing position, because as you can see, because of the sweep wing angle, actually the mass of the fuel is concentrated a little bit backwards comparing to the wing position. Obviously the fuel is going to be located in our wings. Then the power plant is at 7.5, and it usually, this picture is a bit tricky, but at 7.9, and actually they are going to be a little bit forward, just close to the wings. Okay, there's gonna be the power plant, and actually this is a mistake here, it's actually 9.75. okay, so I mean it's not that close to the wings, but it's just a little bit forward comparing to the horizontal and the vertical surfaces. Then as you can see, the horizontal and the vertical surfaces are almost in the end of our body, so their mass is located in the end. And if you think about it, there are some components that are rotating the aircraft forward and some components that are rotating the aircraft backward compared to the center of gravity. And this is what we're trying to do, to estimate where exactly is going to be the center of masses and maybe to reposition our components. So this is it. This is how we chose pretty much the basic components of the aircraft. I'm just going to talk about, for example, the cabin crew. Obviously it is going to be located somewhere on the front. For example, the pilots, the mass of the passengers is always taken in the middle of the aircraft. Okay, and the same accounts for the load. We also take them there here, because usually how we position the passengers depends on how many passengers there are. If there are two, normally we position one in the front and one in the back for the balancing characteristics, if we think that this will make any difference to our total aircraft balancing. And pretty much that's it, guys. This is how we can position the masses. And now let's start estimating our forces and moments. So first we need to estimate the force produced by each component, and the force is simply the mass multiplied by the distance of the origin of our coordinate system. Sorry, obviously this is actually the moment, and the force is simply the mass multiplied by the Earth's acceleration. So here I'll actually estimate first the forces. And as we don't want our forces estimated in Newton, but in dA in Newton, everything will need to be estimated by 0.1. Okay, so I'll simply write here equal to 0.1 multiplied. Actually, you know what I'm gonna do, which is actually going to be quite fast. So here in this cell, I'll actually write equal to 9.81, which is the Earth acceleration, multiplied by 0.1. Okay, and then each cell here we're going to estimate with this one, and I will show how this is done. So here I will simply write equal to the wing mass, the total wing mass, which is this one, multiplied by this mass here. Then the next one will be equal to the fuselage multiplied by this one again. Next, the horizontal surface. So let me find it. So we have the control surfaces. The horizontal surface will be equal to the total control surfaces multiplied by this coefficient here, multiplied by 0.4, because usually the horizontal surface is getting 40% of the weight of the tail, while the vertical surface is more heavy and it takes 60%. So that's it here. Then the vertical surface is going to be equal to, again, the control surface multiplied by the Earth's acceleration multiplied by 0.1 multiplied by 0.6. Okay, and this is basically the force produced by the vertical surface. Then the front landing gear will be equal to, obviously, this coefficient multiplied by the landing gear multiplied by 0.3, because it gets a 30% from the total mass of the landing gears. And finally, the main landing gear will take 70% of the mass of the landing gear, so multiplied by 0.7. And pretty much that's it for the construction of the aircraft. So we're done here, guys. Then we need to estimate the moment, and you can see that the moment is equal to m multiplied by g multiplied, so this is simply the force multiplied by the distance, and this is how we get the moment. So let's write that this one is equal to 7.5 multiplied by the force, and I will drag this down to get the rest of our components. So these are basically all the moments produced by the construction of the aircraft. So that was it for today, guys. I don't want to make this video too long, so I will simply continue in the next one when estimating the power plant, equipment, cabin, fuel, load, and the passengers, the mass of the passengers, and the moments produced by them. So thanks for watching for now, and I will see you in the next video. Hi guys, as I promised, today I'm gonna show you how to balance the rest of the aircraft components, and actually it is quite simple to what we did last time. So let's first estimate the forces produced by the power plant. So this will be equal to the total mass of the power plant, which is this one, multiplied by 9.81 multiplied by 0.1, which is this number here, and that's it. The next one, let's use the equipment here, and this will be multiplied by this coefficient as well. After that, the mass of the front and the rear compartment are obviously half of the mass of the equipment. So usually half of it is positioned on the front and half of it is positioned on the back, exactly for this balance to be feasible. So that's why you can see here the front compartment is quite close to the nose of the aircraft, while the back compartment is quite far from the nose, right? So this will be simply equal to 0.5 multiplied by the equipment mass multiplied by this coefficient here, which will give us exactly half of the equipment mass. Okay, and the same will be here. Okay, so we got the both of the forces are obviously the same, but the moments will be obviously different because they're positioned, the two compartments are positioned in different place. Now the force produced by the cabin crew, we already have it actually, so this will be equal to this coefficient here, and we need to multiply this by the mass of the cabin crew, which is here up there, that's right. So it's 270, okay, the cabin crew mass, and we get for the cabin crew moment about to 64. So sorry, the force obviously produced by this moment. And then I'm actually not going to estimate the masses of the pilot, of the flight attendants, and of the crew luggage, because usually the pilots and the crew luggage are positioned on kind of 2.9 from the origin of our coordinate system, and the flight attendant is only one, so there is pretty much no point of estimating this separately, because I think we would actually get the same value, right? So since we have the total cabin crew masses, I'm not going to estimate this here. Next, let's estimate the mass of the fuel, or actually the force produced by the fuel, and this will be equal to 0.981 multiplied by the mass of the fuel, which is this one, and we're getting for the force produced from the fuel 4,165 dA newtons. Then for the load we have it here, I think. So this is the one, and this will be simply multiplied by 0.981. And finally, our passengers is going to be equal to simply 0.1 multiplied by the Earth acceleration, okay? And I will multiply this by the 12 passengers by 80 kilograms, right? Okay, that's it. And the total force produced by the passengers is 941. Then let's estimate the moments produced by these forces by simply multiplying them to the distance from the origin. So this one will be equal to that, okay? And then I will simply drag this down until here, okay? And then I'll just copy the equation and place it here. And as you can see, this worked. And let's continue. So that's it, guys. I mean, we estimated absolutely every component in the moment produced by it. So now we can estimate the final sum of the moments and the final sum of the forces. And this is quite simple. I will simply select all these fields here, then select this field and choose totals, and from totals I will choose sum. So this is how we're getting the sum here, and I will do absolutely the same with the moments, okay? So here I will choose totals, then sum, and here we're getting the total forces and the total moments produced by the aircraft. So now, as we have all the forces and moments, and we have the total force and moment that the aircraft produces, now let's estimate the force and the moment for aircraft not having a load and not having a fuel, and when the aircraft is empty. So when the aircraft has no load, this means that we simply deduct from the total number, we deduct the load of the aircraft, right? So we're getting 96,000 for the moment in dA Newton meter, okay? And for the force, we're going to get, so I'm gonna deduct it here as well, we're going to get 12,303. Then with no fuel, simply we deduct the fuel, and here simply we deduct the force produced by the fuel, okay? And finally, for the empty aircraft, we would like from the mass to simply deduct the passengers minus the load minus the fuel and minus the cabin crew, okay? And this is the moment produced by the aircraft empty. Now let's see about the force. So this will be equal to the total force minus the force by the passengers, the force by the load, the force by the fuel, and the force by the cabin crew, okay? And as you can see, this is a total force produced by the aircraft empty. So that was it for today, guys, and you can see that for the next lecture we have this small table where finally we're going to find the center of gravity of the aircraft, which means that our aircraft will be completed and ready to pass for manufacturing. Thanks for watching. Hi guys, today we're going to estimate the final center of gravity for our aircraft, and we're going to do it in 3 cases. So for the full, for the no load, no fuel, and empty aircraft. But the first thing I will do is, in your project, I'm actually going to delete this table and place the field table, so you have it in your project. I'm not going to do the same with the workbook, okay? So I will simply place this here and I will actually center it, okay? So now Finally, what we need to do is to estimate the total mass or the total position of the center of gravity of our aircraft. So the first thing I will do is to estimate the coordinates of the center of mass. Okay, so this is simply equal to the total moments divided by the total forces. Okay, and when I do this, you can see that in this case the center of gravity is at 7.82 from the front of the aircraft, which is kind of in the middle of the aircraft, and this means that our estimations were correct, but I will later show you how this looks like graphically. So let's estimate this one as well. So no load, I'm simply going to divide these two guys here. Then for no fuel, we will divide the no fuel estimates, and finally for the empty aircraft, I'm going to divide these two estimates here. That's it. And you can see that we got different positions of the center of masses when we remove masses or we add to our aircraft. But let's see how this looks graphically. So here I draw a simple picture with the masses that we estimated, or actually these were the masses of other aircraft, but now I'm actually going to write your numbers because they're similar. So the no fuel mass is 7.82. Then the full center of masses, so the center of mass of the full aircraft, sorry, with no fuel, it's actually 7.795, right? Then when the aircraft is full, your center of masses is at 7.826, and then when your aircraft has no load, then it's 7.867, and for the empty aircraft is actually quite close to this one, 808, right? 8085. Okay, so you can see that the empty aircraft has its mass quite backward comparing to the other aircraft masses, and we will see how this will affect our final aircraft centering coefficient, which needs to be between 0.2 and 0.3, as you remember. So okay, and you can see here I draw it like the empty aircraft has the center of gravity here. Okay, then the aircraft without any load has the center of gravity in front, then is the center of the gravity of the full aircraft, and finally of the aircraft without fuel. And you can see that this is actually the distance from the origin, which is here. If we will take another origin, for example an origin that is somewhere here, then we will again get the distance from this origin. That's why I told you it doesn't matter in which position you're actually going to choose your origin. So having this, I'm actually going to copy this one in your project so you have it there, and let me place as a picture. Okay, so you have this picture in your project as well. And now, since you found the center of gravity of your aircraft, now what I will do is I will estimate the 5 aircraft centering coefficients, which, as I said, need to be between 0.2 and 0.3. If they are not, we will need to modify some of the positions of our components. But to find them, we first need the median aerodynamic chord and the median aerodynamic chord coordinates. So for our aircraft, the median aerodynamic chord, as we place the wing in the middle, the median aerodynamic chord position will be 7.5. And then the median aerodynamic chord length, we can actually check it from the wing estimates we did early on. So the wing geometry, and we can see that the median aerodynamic chord, or BA, is equal to 0.03. 2.03. So this is 2.03. Okay, so having these parameters, we can now estimate the balancing characteristics, which are estimated with this equation here. So we have XM and we have the rest of the coefficients as well. So for the full aircraft, we will have bracket XM multiplied by the XA, okay, which is the location of the chord, divided by its length. Okay, this number is obviously not logical, and this actually because these two numbers, so the XM and XA are actually not multiplying, but they are dividing. So from XM, or the center of gravity, we have to deduct the position of the median aerodynamic chord, obviously there is no point to multiply them. So I will change this here as well. Instead of multiplication, I will do minus. And let's see. So what we're getting here is 0.16, which is too low number. We need to do something about it. But before that, let's estimate actually the rest of our parameters. So what I will do actually is to write a dollar sign to these numbers here, okay, and I will simply drag this here, and immediately I will get the value for the other coefficients as well. And as you can see, the empty aircraft mass is in the range, but the rest of the masses, they are actually not quite in the range. So we will need to modify this. So if you want to keep the mass of the empty aircraft like this, but change the rest of the masses, it makes sense that we control the mass of the fuel and of the load. So obviously the load is something that we can control. So let's try to move the mass of the load to a different position. Let's move it, for example, to 8. Okay, we're getting better numbers. 8.5. So when we move our load, and this is a very good way to redesign your aircraft, so now you can move simply the masses of the load to different positions in order to have your balancing characteristics fixed. So now what is left to be done is when the aircraft has no load, because we didn't change this mass, but this can simply be done by changing the position of the fuel. So if I write here 7.95, you can see that the no load masses increases, okay? So I will change the mass, the position of the fuel to 8, okay, 8.1. And you can see that now by simply changing some of our components and we reposition them, now we can see that the balancing characteristics are fixed. If you wouldn't do this, our aircraft will not be balanced and there will be way more workload for the pilot, which could lead to mistakes, okay? So this is it, and these are our balancing characteristics, and I'll actually place them just like this in the project because they are very important and they are overlooked by the constructors quite a lot. So these are your final balance characteristics, okay? And this is it, guys. You built your first complete aircraft. There is nothing else you need to know about the design of the aircraft and how to create a project from zero until the end. Thank you very much for watching this course, and I really hope that this course was helpful for you. And whether you were an aerospace engineering student or you're just a person that wants to learn aerospace engineering, you did a very good choice, because I'm sure that if you reach this point, now you're completely familiar with how to build an aircraft yourself. So I advise you, make up another project and just try doing this by yourself. And even if you want, you can send me your project result on Udemy and I will have a look for sure. So thank you very much for watching. I really hope that you enjoyed this course. You can check out the conclusion section, and I will see you in my